There we go. So welcome everybody to this yearly course we're doing on RTA. That's a complimentary course for all Whitson Plus subscribers and everybody that's part of the Well Performance Consortium. My name is Matthias, and I have my colleague Mo here with me today, and I think also maybe Curtis will stop by throughout the day today. The topic today is RTA, so it's going to be very specific to the RTA pieces of both the software and the theory in general from the industry. So I think at the end of the day, it's going to be a little bit of RTA overload. So maybe at that point you'll be glad that it's a whole year to next time we're going to talk about RTA. The theory part, or what I'm going to try to convince you of, is that the theory part of RTA is actually pretty easy. It's the interpretation and getting it to make sense that sometimes can be hard for people. But hopefully at the end of the day today, I've convinced you that the fundamentals are actually quite easy. And it's going to be a lot of information. And the way we're going to do it today is that we're going to basically take the theory part first, divided by a couple of breaks, and then we're going to do the exercises just for those that would like to do the exercises. The data for the exercises, kind of where to upload it and how that's going to be provided. Every time I take a break, you'll see that screen, and I think we'll have a couple of breaks before we start the exercise piece. Great. As I mentioned, the course is recorded, and if you need access to Whitson Plus for this course, we're not going to use your company domain. Most of the folks on the call today, they have access to Whitson Plus through their company. So you're going to go to courses.whitson.com, use your email, and the password is Whitson RTA 2024 star. If you have issues with this, send an email to support@whitson.com if you would like to follow the exercises. That's just if you like to follow the exercises, and I know some of you guys are here primarily for the theory, which is totally fine as well. But just emphasize, this is not your company domain, even though all the things we're going to do, of course, you will also be able to do on your company domain. Excellent. The little kind of context tomorrow, just a reminder that we have these knowledge sharing sessions that we do 3 times a year. 2 of them are fully virtual. The second one that's fully virtual is tomorrow. And then WhitCon is coming up in the 19th of September. And it's primarily just case studies from different operators and also some knowledge share around, if you gave 3 different interpreters the same data set, how would they actually interpret that particular type of data? And these knowledge sharing sessions, they're 100% complimentary. It's primarily operators sharing what they're doing in different basins and with different workflows. And in addition to that, we have these short courses throughout the year. We've done 2 of them already. They're always recorded, and they're on a very dedicated topic. So they're a little bit different from for instance, when I or one of my colleagues come to your office and we do kind of a Whitson Plus introduction course, then we actually do a little bit of a lot of things. Here we're going to do the opposite. We're just going to do 2 things. So if you think about Whitson Plus, it's essentially the focus is just going to be analytical RTA and numerical RTA for the course today. And if you need, or if you'd like to sign up for some of the later courses, if you haven't done that already, just send an email to me. And if you need some kind of certification for petroleum engineering credits and stuff as well, send me an email after the course, and we'll make sure to make that happen. As I mentioned, the main topic of today is RTA. If you want a simple way of thinking about RTA, I know some of you guys on the call, is the first time you probably even heard, not heard the word maybe, but maybe the first time you do an RTA course. So if you want a simple way of thinking about what RTA is, you can think about it as kind of the art or science of combining flowing rates and flowing pressures. So you're just trying to combine the flowing bottom of pressure in addition to the rate versus time data, whether that's oil rate versus time, whether that's gas rate versus time, water rate versus time, total reservoir rates versus time, liquid versus time, etc. There's a multitude of ways to look at it, but that's the kind of the essence, that instead of just looking at rates versus time data, which we're doing in for instance DCA activities, we're also incorporating this flowing bottom of pressure. And there's a few reasons for that, and there's a lot of very good examples of when that becomes very, very important to account for the pressure changes over time. That said, though, it has a lot of, if you've done a lot of DCA, kind of DCA is a special version of RTA. If you do DCA at constant bottom hole pressure, it's essentially, or close to constant bottom hole pressure, it will be very tied to RTA activities. What we're going to cover today is RTA basics. Also, of course, how to use the software if you would like to follow that. And the RTA piece is going to be related to classical RTA, numerical RTA, and fractional RTA. Okay, and we'll assume all the inputs are correct. All this other stuff, we're gonna, PVT, bottom hole pressures, flow measure balance, all these other things that's related. That's we're going to save for another course. And of course, those other pieces are typically a part of a full RTA workflow. But again, the focus of these type of short courses is to make sure we focus on very, very small dedicated pieces of the parts in Whitson Plus and the associated theory. On a lot of these things, you'll see them many times, and we'll also make sure that we go back to a lot of the basics to make sure we have a good foundation to build upon when it comes to both understanding the equations, our objectives with these equations, how they actually work in practice, and some of the key assumptions. I'll also try to keep it fairly practical because we believe in the practical approach. So at least, Mo knows me, Curtis, like all the people that works with me, they know that I'm extremely impatient. So when I learn something, I want to test it out as soon as I can. And if you're in the same boat, throughout the course today, we're going to actually put the theory that we're learning into practice on real wells. And then, of course, when you after the course, it will kind of be your job in collaboration with us to also do that on your all's wells and internal. We also believe in repetition, so a few of the things that you're going to see me do today, we're going to go through more than one time. If you see something more than one time, it probably means that it's very important. So there's definitely a few things that I think we'll go through probably 3 times from kind of 3 different angles, maybe 4 times even. And hopefully we'll see what it is. Maybe we'll do a little quiz on that a little bit later today. When it comes to RTA, if I asked Chris Clarkson, Tom Blasingame, Mike Fetkovich, any of these RTA experts we have out there in the industry, what would be kind of the textbook, quote unquote, definition of RTA? That will be the next slide, okay? That will be the next slide. And the textbook definition of RTA is that RTA incorporates both fluid rates and flowing pressures, and it's used for one thing primarily, and that's to quantify productivity, okay? And there's 2 different productivity terms that we like to talk about in the context of RTA. It's an early time productivity multiplier that many times people refer to as the A root K, also called the linear flow parameter or the so-called LFP. If this is the first time you hear any of those terms, that's fine. We're going to go through that many times today, so don't worry at all. And the second thing is the size of the tank, or what you call this contact to pore volume. Some people call it the stimulated rock. Okay, so you use it to quantify these guys, and you also use it then for well performance comparison, where you actually account for those differences in pressure drawdown. For forecasting activities, either to have a secondary view or to actually validate that some of your forecast assumptions are valid. A good example is, for instance, if you have a DCA forecast, but the DCA forecast has been done while the flow and bottom hole pressure has been changing, essentially decreasing a lot over time, then you know that your DCA forecast most likely will be a little bit optimistic versus if you accounted for pressure, for instance. It's also used extensively for completion effectiveness and frac optimization. So you do RTA activities on a lot of wells, and you try to correlate that with, for instance, different types of completion practices or even well spacing. It's also used for production optimization and drawdown management. You can, for instance, link it to kind of a drawdown type of activity or a nodal type of activity, or you can use it to see, okay, I have this well right here, and we have in some parts of the basin drawn these wells down really hard. Other parts of the basin we've been trying to do a more conservative drawdown strategy. We would like to use RTA to see whether the conservative drawdown strategy or the more aggressive drawdown strategy has actually any imperial like impact when it comes to if I'm losing liquids, when it comes to liquid dropout, for instance, that there's for a gas condensate well, if it's more optimal to stay above saturation pressure for a longer period of time, etc. So that's very common. And then of course, for those that use like more complicated type of modeling, if you build huge simulation models and stuff, it's typically a starting point for some of those type of activity. And there's a lot more that I haven't covered here, but that would kind of be the textbook definition if you talk to someone. The way I like to look at it, very similar to this, but I like to on purpose put RTA into 4 different buckets, and I'm a buckets guy, and I like to organize my world, and I think it helps for you guys as well to think about it in terms of these different buckets as well. The reason why I talk about it is that many times we talk to people, and the people that they've done RTA. I remember when I started with a lot of people, they had done RTA, but it didn't work. And then I was very curious to kind of understand, what did not work, and that was actually related to these buckets. So I'll try to understand that or explain that in a second. But when it comes to these 4 different buckets, I'm going to list them for you in an order of like increasing difficulty. Okay, from simple to quote unquote hard, and all of them, they will use this combination of rates and pressures, and we'll teach you how you do that later. What's the kind of main input to combining rates and pressures? But that if you have that combination, typically referred to as rate normalized pressure or pressure normalized rate, you can do a lot of these activities. And the first bucket is, okay, if you calculate the rate normalized pressure or the pressure normalized rate for one well, you can use it for diagnosing that well specifically, okay? And you use that typically for flow regime identification. Maybe you would like to also identify if certain operational changes are increasing or decreasing your productivity. That's also pressure normalized productivity. That type of diagnostics can be done on one well. You know, those calculations are done in less than a second, very fast. No equations needed for this. It's literally just diagnostic plots where you either provide, you look at slopes compared to the data, or you look at different operational changes and how they relate to those changes over time. So very simple, done in a second. But let's say we took exercise 1 and we put a bunch of different wells on the same diagnostic plot, where all of them have been rate or basically pressure normalized. Okay, then you get just again, no equations, but you get a means to look at all these wells and how they compare to each other from a productivity perspective. And the nice thing now is that you have normalized out for this difference in pressure drawdown, because the different wells can have very different pressure drawdown profiles. So if you compare, for instance, if you compare the cum of a well at 100 days, and let's say they were the same, but to get that cum, you would have to draw down a well 3 times as hard versus another well. The 2 wells are not the same when it comes to productivity. So that's what these diagnostic plots can give you when you also use them on a relative basis. You just compare them to each other. So again, this can also be done in seconds. You just need to have those on a comparison plot. I can show you how that's done in Whitson as well. We'll do that later today. But that's again another use of RTA. It's called RTA. Very hard to fail in bucket 1 and bucket 2. I'm going to be honest with you, and it's very easy to see. I could probably even show it to my mom, which is super smart, but she's not a petroleum engineer, and she could tell me which of these wells were more productive versus another just by looking at these comparison plots. You don't have to need to know any equation whatsoever, any RTA equation whatsoever. You just need to be able to look at a plot and know what is up and what is down. That's it. Then we go into the bucket where it starts to get a little bit interesting, because now we're going to take this data and we're going to try to quantify something. And there's only 2 things you can uniquely quantify from an RTA exercise, and everything else, quote unquote, what we call non-unique. And we'll talk about that in a second. And those 2 unique parameters, if you have PVT, flowing bottom hole pressure, and rates, as this thing that I mentioned already on the last slide, we'll talk many times more about it. It's the so-called A root K and it's the contacted pore volume. If you know what the A root K is and the contacted pore volume is, you know what your EOR will be, okay? Because you know, the EOR is defined as the contacted pore volume multiplied with the recovery factor. And you know, in this case, you will then know what the initial pressure and temperature is. You know what the abandonment pressure conditions would be, or you would estimate that. So if you know these two things, you also can tell what the EOR of the well will be. And this is also a place where, you know, we might maybe have a few different interpretations of what the A root K and the contacted pore volume is for a given well, from one engineer to another, but not huge. Where I see a lot of people in, you know, where they've done RTA and they've burnt themselves, and after that they've said, I've tried RTA and it doesn't work. That's when they go from number 3, which is quote unquote unique, to number 4. And number 4 is that you use RTA to resolve physical parameters, such like fracture half length and permeability. And if you know what you're doing, if you know all the assumptions that you're making, and those assumptions are reasonable, that's a totally legit thing to do. But if you're not comfortable with those assumptions, or if you don't even know what assumptions you're making when you do that, that's when it becomes dangerous. And that's where I've seen a lot of people have been burning themselves in the past on RTA, and also where people have maybe lost faith in RTA because they're like, I did it and I got this XF, it does not make any sense. That's kind of the most extensive and advanced bucket. And what you basically do there is that you take what you call A root K on this contacted pore volume, and you make some assumptions of how many fractures you have and what your fracture height is. You also assume that you're in full boundary dominated flow, and you also assume that your fractures are perfect rectangles, which in reality we know they're not perfect rectangles. So that, like in number 4, that's a lot of the assumptions you're actually making when you're resolving an XF and perm. And if those assumptions going into it, if your fracture height, it doesn't make any sense, if your fractures are not actually perfect rectangles and whatnot, then using RTA to resolve these physical parameters is something you should be careful with. But if you know what you're doing and you're comfortable with your assumptions, you'll be in really good shape on number 4. So these are the 4 buckets. Now, number 1 and number 2, we can do those very fast. It's going to take seconds. And then number 3 and number 4, at least if you would like to do the full numerical workflow, they would take maybe up to 5-10 minutes per well, if you get good. Core piece of RTA is this quote right here, at least for me, is that it's better to be roughly right than precisely wrong. And it goes back to this thing that there's a difference between, call it precision and accuracy. So you use very readily available data, you use models that are simple enough, but they explain enough of the fundamental physics, and you get really good history matches, and you're able to explain well performance really well with these models. And we typically kind of teach and go through an unconventional reservoir workflow where you go and calculate PVT properties, you calculate bottom pressures, you do an FMB exercise, which we'll not talk about today. And then the RTA piece is kind of the key piece before you bring it into a numerical model. And the emphasis of the course today will be kind of these two last pieces right here. And I see we have a lot of people here today, which is fun. And I also know, just because I've talked to many of you guys before leading up to this course, and for the folks who showed interest in the course, that you know, this is your first RTA course. And then I know there's a lot of people who have done extensive RTA in the past as well. But for at least the new people in the audience, when it comes to RTA, there is 2 slides in this deck that's going to teach you everything you need to know about RTA. And that's the next slide and the slide after that. And that goes back to what I would like to try to convince you of, is that RTA is pretty simple. The theory is really simple. And if some of us educators have convinced you otherwise by starting the lectures by I guess deriving a super complicated equation, I think we've failed. Because it's actually no matter how difficult the equations is, the objectives are always the same. So if there's 2 slides you want to pay attention to, for at least the ones who haven't done RTA before, it will be the next slide and the slide after that. And the first thing you need to know when you do RTA, at least have an opinion of, and that opinion can change when you get presented more data. That's totally fine. Or if you talk to a colleague or whatever, and you know, changing opinions are great, but you need to have an opinion when you look at a well. What flow regime do I think this well is in? And there's three different types of flow regimes that we typically talk about in tight unconventionals. And that's infinite acting flow, boundary dominated flow, and in between what we call transitional flow. So the first bucket of flow regimes, what I talked about as infinite acting flow, that ends as a pressure transient had reached one of the reservoir boundaries. And that's super relevant for these tight unconventionals because the permeability is extremely low. So pressure transients are moving very, very slow compared to a conventional reservoir. So you can have extremely long periods where you're essentially infinite acting, or parts of your reservoir is infinite acting. That period is called infinite acting flow. The total opposite extreme of that is what we call boundary dominated flow. That's what we learned about in school. If you've done reservoir engineering in school and you remember the term pseudo-steady state, at least that was what they taught when I was in school, or they also called it tank-like depletion, and boundary dominated flow, it's all the same thing. Pseudo-steady state, boundary dominated flow, tank-like depletion is the same thing. And it starts when the wellbore pressure response is affected by all the reservoir boundaries, okay? So I think everybody here sees that these are two extremes, right? Infinite acting flow, I'm not feeling any of the boundaries. Boundary dominated flow, I'm actually starting to feel all the boundaries. So if I was a well drain in the room I'm sitting in right here, in infinite acting flow, I don't even know that the walls behind me and to the right and to the left of me, etc., is there. But in boundary dominated flow, oh, I know, I've seen all these walls at this point. Okay, so these are the two extremes. If you want to put this into a DCA world, if you do a lot of declines, you do a lot of resource evaluation and whatnot, you know, the B factor you're using in the ARFS equation, if you would like to link that to infinite acting flow and boundary dominated flow, you can also think about those as extremes. So for constant bottom hole pressure, infinite acting linear flow for low compressible fluids, so that will be single phase oil or single phase water flow, that will be a B factor of 2 in infinite acting flow. And if you're in boundary dominated flow, your B factor will be 0, okay, for the same scenario. Constant bottom hole pressure, low compressible liquid in full boundary dominated, okay? And in between here, we have a very important flow regime that's super relevant in unconventionals, which is called transitional flow. That means that we're not in 100% infinite acting linear flow, or infinite acting flow, but we're also not in 100% boundary dominated flow. So you might have seen some of the reservoir boundaries, but not all of them. And that means that, you know, some parts of the reservoir is in boundary dominated flow, some is infinite acting, and at the wellbore you're getting this mixed signal. So that's why many times, like, you want to think in like B factor space again, even at constant bottom hole pressure, you can have B factors that are not 2, they can be higher than, you know, 1, 1.2, 1.3 for a very long period of time. So people are like, yeah, what is the reason for that? And that can be explained that you're actually in transitional flow. And we'll take a look at some wells that's in transitional flow. So that's the first thing you need to do. You need to define, okay, is my well in infinite acting, boundary dominated, or transitional flow? And you also need the tools to be able to, you know, look at wells and say, this is infinite acting flow, boundary dominated flow, or something in between, which is transitional flow. And that is something we'll teach you later today. What's the diagnostic plots? What are the tools you'll need to be able to make this assessment? Okay, so after we've set what, and you'll understand why it's important to have this opinion, because it actually has an implication to what we can quantify from RTA. And that's the second slide that's important. What can we uniquely derive from RTA? And there's only 2 things we can uniquely derive from RTA. If you have initial PVT, bottom hole pressures, an RTA. And it's your A root K parameter, also called the linear flow parameter, and it's also the so-called contacted pore volume, or some people call it the stimulated rock volume. That's so some people call it the contacted OGIP or the contacted oil pulse. And this is important, if you guys are taking notes, the linear flow parameter, also called A root K, that parameter is correlating with short-term productivity. When think about it simply, correlates with 3 months cum, year cum, etc. While the contacted pore volume is what correlates with EUR, okay? So the contacted pore volume will correlate with EUR because the contacted pore volume multiplied with the recovery factor is the definition of EUR. So sometimes if you have, you know, I've seen some papers and stuff where they present some relationship between their EUR and their A root K. That's totally fine, but behind the scenes, then it must physically be a correlation between LFP and the contacted pore. Second point here is that A root K is something you can uniquely define when you observe infinite acting linear flow, okay? So think about that a second. You can't quantify the true A root K if you do not observe true infinite acting linear flow. And the same goes on the contacted pore volume, that you can't quantify the full contacted pore volume unless you're in full boundary dominated flow. So that's why these flow regimes are very important when it comes to quantifying these two things. So RTA is nothing more than that, flow regime and quantifying these two things. And that's what you need to know, to be dangerous at least. 99% of it. All the other stuff is you have to be a good talker. So if you want to put this in, if you want to explain to management, for instance, you know, or someone without a engineering background, like why do we need to do RTA on our wells? A very powerful slide, I think it's this slide right here, that was presented by a friend of mine, Sam, when he was at Callan, I think. That if you have a well with a high initial production and a high EUR, it must fundamentally have a high A root K and a high contacted pore volume. If the IP is low, but the contacted pore volume is high, you can still have a large EUR, but the IP will be low. A small completion will be down here, and then overstimulated rock will typically be up here too. And this IP, you know, this typically first year of cumes or something along those lines, early time period. This is of course simplified, but it's a very powerful way to explain RTA so feel free to steal this slide if you want, or you know, steal it from someone that stole it already. The way we quantify this contacted pore volume is in a few different ways. We'll talk about that in a second, but I just want to make sure that we're all on the same page when it comes to this volume, this contacted pore volume that we're solving. So basically, when we're doing RTA, we're estimating a volume, a tank size, and that tank size should not be confused with what you've mapped petrophysically, okay? So...
But yes, I think there's a question just before you get there about the LFP that you calculate, the K that you calculate from the LFP, if that's the reservoir permeability. You can comment on that.
Yeah. So so from the LFP equation, there's a K there that you So was it the question from Jackie there, Mo? Yeah. So we'll talk about that a little bit later, like the geometries that we're assuming and what they mean. But that will be the reservoir permeability, at least in the terms of that model. If we call that matrix permeability or SRV permeability, etc., that's more of a function of what your mental model is. But we'll talk about that a little bit later. But you need to actually have both the contacted pore volume and the LFP to be able to calculate what the permeability is from RTA. You can't just have either or. So you need to have both of those guys. But it comes out from that equation. That's correct. And we'll actually show you guys later how those equations are derived and why you need to know the first thing before you know the other thing. This contacted pore volume, that is kind of the secondary piece coming out of RTA. The reason why it's very important for me to emphasize that it's different from the petrophysically mapped in place volume is if all of us, we went out to to the Bakken and whatever, and we came up with the surface area, like the drainage area or the lease area, let's call it the lease area, and we multiplied that with the reservoir height, and we adjusted it for water saturation and the porosity, we would know what the full petrophysical in place volume is. That's this gray box right here. But in unconventionals, we're essentially creating our reservoir, and that reservoir, after we put a few wells in it and we go in and stimulate that rock, we're not able to contact everything that's there in place. We're able to contact a subset of that. And the volume that the RTA exercises and also flow material balance exercises are resolving for you is whatever you're able to contact, which means if you want to think about it simply, it will be the part of the reservoir that you, over the lifetime of the well, will be able to, like over 50 years, you will be able to draw down the pressure there to the abandonment pressure. So that's the at least an intuitive way of thinking of what this volume is. So it's whatever the well is seeing, and not necessarily all the volume that's down there. Okay. So there's an important difference between the petrophysically mapped in place volume in gray and the volume that you resolve from an RTA exercise, which is the contacted pore volume. And the well only knows whatever it just uses the rates and pressures, and we'll just be able to resolve what it's actually seeing, and not everything that's not contacted. Some people call this also the stimulated rock volume or the drained rock volume. If you're interested in knowing why we call it the contacted pore volume, ask me a question in the break and I'll explain you why. But on purpose, we call it the contacted pore volume. And the contacted pore volume can be quantified in multiple different ways. You can use the reservoir volume. You can use the surface volumes, like in oil in place or gas in place, or even water in place. But I think most commonly people are using oil in place for an oil, gas in place for a gas. And I've never seen anybody using water, but it's all the same thing. It's pore volume multiplied with PVT property. So it's all the same, but it's different. The second thing I wanted to just try to explain a couple of things around is this concept of boundaries, reservoir boundaries, 1D models, 2D models, 3D models, and flow regimes. So a very fundamental model that is used in these exercises, both RTA exercises when you've derived equations, or even in numerical exercises, if you use symmetry of elements and whatnot, is this very simple geometry right here. This is a numerical grid that is flowing. There's one direction of flow. There's no volume beyond the frac tip or the frac height, and the flow is going from the matrix into the fractures. That means that since you only have one boundary, it's called a one-dimensional model, and you will only have two flow regimes. The flow regime would be infinite acting flow followed by boundary dominated flow. So either you see the boundary or you don't see the boundary. And if your fractures were perfectly spaced out along the lateral, and it would be there would be exactly the same frac length and frac height, etc., then even though you have multiple of these, it's still a 1D model. It has one boundary, it's one-dimensional, and it has two flow regimes. This model, though, if I start to include some more complexity, so a very simple way of including complexity is just to add a little bit of fracture reservoir volume that's unstimulated. So in this case, we have stimulated reservoir volume here and a little bit of non-stimulated reservoir volume beyond the frac tip. And if you do that, now you're actually having a so-called two-dimensional model. So you actually have two boundaries. You have flow from the sides going in and from the outside going in as well in the unstimulated rock. And the number of flow regimes that we'll have is first you're infinite acting until you see any of the boundaries. Then you go into transitional flow, and then until your whole non-stimulated rock volume here is depleted, you will not be in at least a rigorous definition of boundary dominated flow. People would probably call that apparent boundary dominated. And I know we talked a lot about flow regimes, so I'm not going to take too much on it. But if you think about this ordering of flow regimes that we can have, you have infinite acting, transitional flow, boundary dominated flow, and they need to follow some sort of pattern. You will know that for a given well, there could only be I think 9 or 7 different scenarios, and that will be these ones. So you either are observing, when you look at a well, it's either an infinite acting, and it has been an infinite acting for the entirety of the observed history, or it's initially infinite acting followed by transitional flow for the rest of the observed history, or it's initially infinite acting, followed by transitional flow, then finally followed by boundary dominated flow, or it's initially infinite acting followed by BDF, no transitional flow, or you can have transitional flow for the entire history, or initially transitional flow followed by boundary dominated flow, or actually boundary dominated flow for the entirety of the observed history. Okay, so these sequences are basically the different ones that you could have. I would say a few of them are less common than others, but at least these are the different kind of sequences of flow regimes you can see in these type of equations. And before we're going to take the first break today, and then we've actually covered a lot of the introduction theory that we're going to talk about is RTA in a nutshell. So I'm going to go through the essence of the course today in probably 15-20 minutes. And what the essence of the course today is, we're going to cover classical RTA. And classical RTA involves the use of the square root of time plot. Many times it's from this famous Bob Wattenberger plot in the late 90s, and it's been kind of the driving or kind of the main engine, if you like, or the one of the most used plots in the whole RTA space for a very long period of time. We of course have it in the software as well, and people like to refer to this as quote unquote traditional or classical RTA. Then we have numerical RTA. That some people call that the Bowie workflow. Was presented by Braden Bowie at the PASH a few years ago, and has become extremely popular the last few years because it essentially is using a lot of the same assumptions as classical RTA, but it also solves for some of the main problems. So we'll talk about what those main problems is in a second. And then around the same time, actually, you know, Jorge Acuna at Chevron done a lot of fantastic work related to fractional RTA, which is a very elegant way of extending classical RTA into accounting for more complexity without making the models that much more complex. And it's using a so-called delta term. So these are the three different types of RTA we're going to talk about today. And I'm going to, in a nutshell, try to explain the difference. Then we're going to go through it one more time and a little bit more in detail. So at least before we do the exercises, you've seen stuff 2 times. And when we do the exercises, we're going to take ourselves to look at the data, look at these modules, and look at how the pieces are actually playing together in practice for real data. We start with classical RTA, where we use this plot called the square root of time plot. And just to focus on this, of course, this is a cartoon. It's not real data, but it's just a cartoon of the square root of time plot. And the square root of time plot has on the x-axis, instead of using time, we're just plotting the square root of time, and everything here is Cartesian. And on the y-axis, we're plotting basically the rate normalized pressure called the RMP. Okay, so that's we'll define that later in the course if you don't know what it is, but I'll mention it here we'll just mention it here one time. The delta between initial pressure and the flow and bottom pressure divided by the rate that day. Okay, so we'll talk about that later. That's the moving pieces and what you're plotting on the plot. Everybody on this call, at least for a primary fluid, if they have the rates and flow pressures over time, can create this plot in Excel. Very easy. And when you use this plot to interpret data, your job is to find a straight line portion of the data that is associated with a half slope on another plot that we'll talk about later. And that slope will give you your A root K. And the second thing you're trying to identify is when there is a deviation from the straight line, we will actually call that the time to end of linear flow. That's where we get our contented parabolic. So again, back to what we talked about initially, RTA is 2 things, A root K and time to end linear flow. The slope gives us the A root K, and then the time to end linear flow gives us the size tank or the contented parabolic. So the first thing that's important is of course the slope, and the second thing that's very important is this time to end linear flow. And we'll actually look at the equations later. For now, you're going to get the kind of cartoon explanation. So if we look at the slope, when you plot this rate normalized pressure versus the square root of time, that slope will have a relationship to your productivity, actually an inverse relationship to the productivity. What we're plotting here on the y-axis is the so-called rate normalized pressure, okay? And the way you define it is that you take the delta, so this is the initial reservoir pressure, and you subtract the floor and bottom pressure, and you divide by the rate. This is constant, this is changing every day, this is changing every day. And everybody here can do this in Excel, I'm 100% sure. And the slope is directly relatable to the A root K, so or the so-called linear flow parameter. This is a small LFP, this is a big LFP, and this is a bigger LFP. So productivity is essentially increasing here. So you can imagine if you had you can plot multiple wells on the same diagnostic plot, and you would see which of the wells are actually more productive versus the other. In a similar manner, the time to end linear flow is related to the tank size. So the longer it takes to reach boundary dominated flow, or the time to end linear flow, the larger your pore size is. This will be, or not pore size, the tank size. So this will be a small oil in place, this will be a big oil in place, and this will be an even bigger oil in place. That's how fundamentally the 2 moving pieces here are working together. And we'll look at the equations a little bit later. But now you know at least the fundamental. The second thing is the numerical RTA piece. And I think all of you guys already know what the RTA piece is. At least the RTA piece is we want to quantify A root K and we want to quantify the contacted pore volume. The numerical piece just says that we're going to do that instead of using the square root of time plot, which is an analytical technique. We're going to actually tease those parameters out from a numerical model using what we call numerical RTA. And the problem that it solves is that all the analytical equations, so like from this Bob Wattenberger plot and the equations we have in our software and that we're going to go through in this course, they assume a single either constant rate or a constant pressure solution, and they also assume single phase flow, so one phase flowing at a time. While in reality, we know that we're not only dealing with one flowing phase at a time, but we also know that we're dealing with, or more than one flowing phase. We have oil, gas, and water many times free flowing in the reservoir, and that's what we call multi-phase flow effects. And in addition to that, we know that both rates and pressures are changing over time. And that's what we call superposition effects. And that combination of superposition and multi-phase flow effects, that's impossible to solve for analytically. You can't solve for it analytically. So, but a numerical model can actually pretty easily do that for us. So we kind of say everything that's hard, we can give that to the numerical model, and then I'm going to actually go in and tease out those two parameters myself. The problem that was observed, so this was observed on real data in the Midland Basin, that's oil wells, where they would plot the square root of time plot, and they would plot points above the bubble point, and as soon as you reach the bubble point, this plot would start to skew upwards. And what happened is that as you go below the saturation pressure, gas is coming out of solution. You have this combination of multi-phase flow and superposition effects that even though you haven't seen a reservoir boundary, that plot will start to skew upward. So if you did the classical RTA workflow would be to put a slope here, and you would go in and find a time to end a linear flow. That time to end a linear flow, if it's not a true reservoir boundary, you'll pick it's too small of a tank size, which always will lead to higher permeabilities or to brackish half lengths and justify more wells per section. And I think you guys know the story from there. So what the numerical RTA gives us, this Bowie diagnostic plot, we'll talk about that in the software a little bit later, is that it teases out for us a so-called LFP versus time plot, where a flat horizontal line indicates infinite acting linear flow. Deviation below this line represents boundary dominated or transitional flow, and the magnitude of the flat line itself indicates the LFP. And this right here will be quote unquote the time to end a linear flow. The second thing that it does is that you run at the same time a wide range of numerical models. The only difference between those numerical models is the size of the tank. You're choosing not only the LFP, but you're also choosing the tank size that's closest to your observed data. So what have you done? You picked an LFP and you picked in contacted pore. You've done RTA, but you just used a numerical model. This came from a Zurich paper a couple of years ago that you can read about here. And it's exactly the same stuff that if you've done classical RTA using the square root of time plot, square root of time plot will give you your A root K, and the contacted pore volume comes from moving that line, the time to end a linear flow line, to the right or to the And some of the inputs to numerical RTA, that's PVT and production data, but all these numerical models, they will also require rel perm. So that would be kind of a history matching parameter or something that you would like to change, and you hopefully would like to keep them pretty similar, or at least wells in the same area, because relative permeabilities is kind of like combined rock and fluid type of data set that's very hard to measure. And it's not like PVT or bottom pressures where you can kind of calculate it at least with some accuracy if you don't have the data available for it. Last thing I'm going to do just quickly before the break is to talk about fractional RTA, where fractional RTA, what it solves is that all these classical RTA models, they assume equally spaced fractures, while in reality, we're dealing with something that's more complicated. That could look something like this, or it could look something like this. Doesn't really matter how it looks like, but this is what you call uneven frac spacing. Uneven frac spacing was highly popularized during these ConocoPhillips papers in 2016, also called the $30 million papers. The hydraulic test sites studies that's been done, where you basically see a lot of the fractures, maybe due to inefficient cluster efficiency, or sometimes you actually get more fractures than perforation clusters, that you will have uneven frac spacing, meaning that these will go into boundary dominated flow first, together with these guys and these guys, but in between here, there'll be an infinite acting signal, because this at least for a period of time, And in that period at the wellbore, you're seeing this mixed signal of infinite acting and boundary dominated, and that's what's called transitional flow. So what fractional RTA is doing and helping us with is, classical RTA gives us A root K, and if you remember back to school, A root K, that's, you could put that K up to 0.5. I think everybody remembers that. I'll let, at least now you've been reminded. And fractional RTA, which comes from Horia-Kuhn, solves for a complex system of fractures that gives you a K to the delta. And if that delta is 0.5, it's the same as we've always done. If it's something more complicated than that, or a different value of that, it just is representing something more complicated. The LFP in that sense is not A root K, it's just AK to the delta. How do you get delta? You get that from essentially the same plot we just looked at. It's just plotted not versus square root of time, just versus regular time. And you plot it log. And when you plot it log, you can fit a parallel through that data, and that delta parameter right there, that is your delta. So a delta of 0.5 back to flow regimes, that's infinite acting linear flow. Delta of 0, that's boundary dominated flow. And transitional flow, that will be a delta between 0 and 0. With that, I know we are a little bit early actually on this, but I think we're in really good shape on the theory part. And what we're gonna do is, after this, we're gonna look at these things a little bit more in detail. So you've seen it twice before. We're gonna run through the theory or the software exercises. I think at this point we're gonna take a break to 9:10 Houston time. So we're going to give it 14 more minutes. That's primarily for myself and my voice, because I've done this enough times now that I know that if I talk too much like this, it's going to be take a toll on the voice a little bit. So we'll be back here in 14 minutes, and I'll just make sure that I stay muted in the meanwhile. Okay, we'll get started again. So for the next hour, what we're going to do is we're going to try to take the topics we talked about, which is classical RTA, numerical RTA, fractional RTA, put a little bit more meat on the bones. But just remember that all the fundamentals, they are still the same. We would like to get a contacted pore volume, and we would like to get a root K. And I hear a little bit of background noise on one participant. I think that helped. Okay, that should be good. So hopefully everybody can see the screen again. This will, I think, be the last hour with the theory part. And then I'm going to go into the software exercises for those that would like to follow those. So again, RTA, we repeat this a second time. We can uniquely derive an A root K and a contacted pore volume. And typically the A root K part correlates with 1 year cums, and the contacted pore volume will correlate with UR. And the A root K, that's something we observed during infinite acting linear flow. And then to really quantify the contacted pore volume is something we observed during boundary dominating. And what is A root K? Well, if you have done a lot of conventional wells before, I don't know if you remember back to school, if you've worked a lot of conventionals, they would talk about KH. What is the KH of the well? It was something that was very important, I remember back then. And you can think about A root K as kind of just a sideways KH. So instead of hunting for KH, well, like a larger KH would be beneficial. We're hunting for we would like to have a larger A root K. So that's, if you want, kind of an intuitive way of thinking about it. The conventional way of defining the A root K, or the so-called LFP, would be this equation right here. So it will be 4 times the number of fractures times the fracture half length times the H. So it will be basically this, if you see that with animation there, whatever the surface area is here. Some people ask sometimes, like, okay, why? Because the area of one of those plates, it's 2 times XF times the H. So why is it 4? The reason why it's 4 is because there's flow from 2 sides. So that's where the last 2 comes from. So there's 2 times NF, XF, H, multiplied with the square root of permeability. And that's the definition of A root K. And again, I know that some folks are asking some questions in the chat. So just, hopefully Mo can let me know if there's any questions here that needs attention, because I can't see both screens at the same time here. The other one is the contacted pore volume. So that's the size of the tank, what you've been able to stimulate. And at least for this type of geometry, that would be 2 times XF times the length of the well, times H, times the porosity, and you adjust for water saturation. So this is an example for oil and gas. So that would be, how big is this box right here? Those are the 2 things. And then different RTA methods, whether you use classical RTA, numerical RTA, or fractional RTA, they in some cases, they can give you different ARID case. And good examples of that is like, okay, classical RTA might be looking at only one phase. It assumes constant PVT properties, etc. While numerical RTA is looking at all the free-flowing phases. And then, fractional RTA would be the same as classical RTA, but only when the delta is equal to 0.5. So when it comes to like comparing different outputs from these different methods, you can do all of them, but make sure that when you compare ARID case from classical RTA, you compare them with ARID case from the other wells on a kind of consistent basis, such that you don't mix and match too much, because there's good reasons why they are not the same. Okay, but they can still extract value from all the parameters. So we're going to do a second kind of deep dive into classical RTA, and that's to make sure you actually know what's going on when you're moving lines around on the classical RTA plots. A very key assumption in classical RTA is that we're assuming a so-called symmetry of element model. That's what we call a so-called one-dimensional model, where there's only one no-flow boundary. So that means that there is no volume beyond the frac tip or beyond the frac height. So that means that in that world, there's only 2 flow regimes as well. It's infinite acting and boundary dominating. And if you look at this plot again, we'll see that typically the way we do RTA, we plot the so-called square root of material balance time. There's a couple of other options as well, but we'll talk about that later. We plot that versus rate normalized pressure. We generate a slope. That slope gives us the ARID K. And then the time to linear flow is what gives us the size of the tank. So we're going to try to break down all these pieces a little bit more in depth. And we're going to start with material balance time. And material balance time is very common to use in rate transient analysis. And the method is the so-called superposition time function, which means that it converts variable rate data into an equivalent constant rate solution. Okay, so it takes changing rates and pressures into a world where everything is constant rate. Okay, a little bit abstract. It's rigorous for boundary dominated flow, and it also works great for infinite acting data as well. And the beautiful thing about it, like when Blossengame and these folks came up with it, is that it's very simple. All of us can do this in Excel. You just take the cube until a given date, and you divide by the rates, and you get the units of days. And that's what you essentially are assuming is your time. So that's material balance time for you. So, and there's a couple of other options too, but this is the most frequently used one. Then on the y-axis, we're plotting rate normalized pressure. This is the second time we're showing it. And rate normalized pressure is very useful for production analysis, where the flowing pressures and the rates are changing over time. And the rate normalized pressure is just defined as the flowing pressure drop divided by the rate. Okay, so it's the delta between initial reservoir pressure and the flowing bottom pressure that day divided by the rate. Okay, so good so far. This is what we have on the different axes. This is the y-axis. The other one, material balance time, is the x-axis. And then we use these, and then we're going to come into the equations. And this is where hopefully I'll not lose you guys, but maybe could be good to pay a little bit of extra attention on the next slide. We're using this equation for to extract the slope. So that's where number 3 here comes in, right? So we have the slope, that's the thing in black, call it M. And then in this case, you see we have a subscript called CR. And the subscript just refers to constant rate. And that's because these equations right here, these analytical equations, they are analytically derived assuming constant rate. Okay, so this requires a little bit of explanation. So if you remember back to school when you did calculus, for us that do remember, it's getting further and further away. But if you remember back in those days, when you had to derive especially in calculus, a little bit advanced calculus, when you had to derive some kind of relationship, you had to assume what was called a boundary condition. And that boundary condition, when you derive these analytical equations right here, you can choose whether you would like that to be constant rate or if you like that to be constant pressure. And you would kind of think, or you would kind of assume that my assumption of constant rate and constant pressure shouldn't really matter. The problem is that it does. And the equations, they look really similar, but the constant rate equation and the constant pressure equations, they're different by pi divided by 2, so pi halves, which is 1.57. So they're almost like 60% different systematically. All the parameters are the same. It's just that for constant pressure, this guy right here would be multiplied by almost 60%. So it will be closer to 30 up here and closer to, I guess, 300 up here, or a little bit more than 300. But in this case, since we've used material balance time and we converted everything into a constant rate space, it's consistent that we're using the constant rate solution. Okay, so it wouldn't make sense to use the constant pressure solution in this case. So if we use material balance time and these equations, it is consistent from that perspective. Okay, but that's why we talk about this constant rate time right here. And I remember back in school when all these topics were kind of difficult for all of us, I think. And but I had a Greek gentleman in my class, a super smart guy. Like it was obvious that Greece was the home of Pythagoras and all this stuff, because he was, at least mathematical equations and analytical equations, he ate them for lunch. But I remember every time he got a very difficult question and in class, from the teacher on reservoir simulation and stuff like this, and nobody would answer, he would just raise his hand and he would say, well, it's obvious. It's the boundary conditions. And again, here, like, boundary conditions really matter. Like, where do you put your boundary? And also when you derive these equations, boundaries, whether it's constant pressures or constant rate, which is a surprise for a lot of people the first time they hear it, actually has a huge impact on the resulting equations. But as long as we use material balance time and we use either of these equations, we should be in good shape. And for gas, we typically use something called pseudo pressure, and that's because a gas can be highly compressible versus a liquid. So that's why we use something called pseudo pressure. That's basically just to try to linearize those equations also for gas, so that we can use the same concepts. But very importantly for this is the slope, this MCR. That's basically this guy right here and this guy right here. And I know there's a lot of terms here that can confuse us, but if you look closely at this equation, this is just an intercept. Let's forget about that. But if you look closely at this equation, it's PVT properties, and it's essentially the LFP. That's what this is. This is PVT and LFP. So you see that from the, you have already assumed PVT when you do RTA. So, they're given, and you assume the processing. So this is where the LFP parameter comes from. So that's what I'm saying. Your slope is essentially your A root K. It's how you determine, calculate, or estimate the A root K. And then where does this time to end a linear flow guy come in? Well, the time to end a linear flow is the exact equivalent for linear flow to the radius of investigation equation that maybe, at least that was a very, very common or fundamental in the reservoir engineering courses I did in university. It's the same thing, it's just for linear flow. Okay, so that equation, the time to end a linear flow equation, is the second equation that's needed to get all the pieces to fall in place. And that equation looks like what we're seeing here to the right, where you basically have the well lateral length. You have assumed the number of fractures. This is PVT and porosity. And when you have picked time to end the linear flow, there's just one unknown here. Everybody sees that? Only one unknown, and that is K, because I've assumed everything else. And this is also going back to, there's no XF in this equation. So a lot of people come to me and say, if I increase my NF or decrease it, it only impacts my K. What about XF? I would like it to impact my XF, but that's not how the equations work, unfortunately. And you'll see that you'll meet yourself very, very soon in the door if you put that into an Excel sheet and you try to solve for those equations, because there's two equations and two unknowns. And when it comes to permeability and NF, that's two sides of the same story. So the only way to potentially increase your XF would be to change your content of core volume to a larger number. Okay, so once you pick the K comes out of this equation. and then you plug K back into this guy right here, and this is the slope, and there's only these two unknowns in the slope, and that's what gives us the contacted pore volume. I've already assumed porosity and lateral length, and these ones are now solved for when I've solved for K. So I put K in here. The only two unknowns is this combination right here, and that's how I get my pore volume. Okay, so that's how it all is plugged together. If we repeat this one more time, the slope right, this plot right here, it's a working horse of classical RTA. It's been that for 25 years probably, 25 years probably now. It's not that many moving pieces. Everybody here can code this up in Excel even. It's pretty simple. We use material balance time typically in most stuff related to RTA because it's simple, but it also converts everything into constant rate. And we combine that with rate normalized pressure and these equations that are constant rate equations. And then we combine it with the equation of a time to end linear flow. That's how we solve for K, which is what we plug in here. And we only have the HXF, which is the area piece, right, that we plug in here. That's how these things are moving together. And for you, you need to know that when you move time to end linear flow to the right, you're increasing the pore volume, and to the left, you're decreasing it. And the same goes with the slope. When you increase the slope, you're reducing your A with K, and vice versa. When you do analytical RTA, it's very common to also look at, you remember on the y-axis, we plot rate normalized pressure. If you just change those upside down, it's what we call the so-called, the inverse of that. That's what we call the pressure normalized rate. And that's just the inverse of rate normalized pressure. And it's very useful for production analysis where flow pressures and rates are changing over time. And it's defined as the rate divided by the flowing pressure drop. So it's basically this guy. And many times this can be a really helpful diagnostic, at least if you talk to the experts on RTA. You typically would like to look at where your half slope is on the PNR plot, because that should correspond with linear flow. And that's where you should, if you see deviation there, that deviation should correspond with your deviation in the square root of time plot. So that's why, like in Whitson, which we'll talk about later, you have the square root of time plot here. And this is rate normalized pressure versus square root of time. And then we have pressure normalized rate here, which is just an inverse. And here you would like to add a slope from when it's a half slope, such that you're not only picking a straight line here, but you're also picking the straight line when you're actually in infinite acting flow, because that's what you need to quantify L. Okay, so if you look at this dashboard, this is rate normalized pressure versus square root of time. This is just rate versus time. And this is pressure normalized rate versus time. This is just pressure versus time. Also, now we're starting to increase the difficulty level a little bit. But if you see in the screenshot right here, and you'll see this in a lot of features in Whitson, that there's an integral function here, and that there is a derivative function here that you can activate in the plots. And the derivatives and the integrals, they're really helpful, and they come from kind of the grandfather of RTA, which is PTA, right? Well testing. And well testing is the same as RTA, just well testing, the rates are 0 typically. And you're analyzing the pressure signal, okay? And there, when you analyze these pressure signals, it's very common to use derivatives of pressure and the integrals of pressure. And that's also common to use, or can be powerful to use when you do use analytical RTA as well. And in general, these derivatives, they amplify the reservoir signal, but they also amplify the noise. Okay, so if you have clean data, you'll be able to pick up reservoir signals much sooner with the derivative than if you had just the raw data itself. So here you see an example in Whitson where we toggled on the derivative, and you actually see that it's starting to pick up full boundary dominated flow here versus somewhat later here. It's very much more sensitive, if you like. But if the data is pretty noisy, you can see that it has some implications of the usefulness of the derivative, and vice versa. Like an integral, like in PTA, they use this Bourdais derivative. So the Bourdais was a guy from Schlumberger, and he founded Kappa back in the 80s, and unfortunately passed away in the very early 90s. But that Bourdais derivative is a log derivative, very fancy and famous to be used in PTA, and is also used in RTA as well. The other side of that is, okay, instead of using derivatives, let's use integrals of rate normalized pressure or pressure normalized rate. Okay, and these integrals, they reduce the noise, but on the other side they also reduce the signal. Okay, so derivatives, they're amplifying the signal and they amplify the noise. Integrals, they reduce the noise, it amplifies the signal, or reduces the signal. Sorry. So this is the raw data, and this is a case where we just applied the RMP, or basically the PNR integral right here. Okay, and it will just clean up the data, but you can still use the functionality as is. We'll take a look at this a little bit later, but it's useful for you guys to know. And it's the same in the flow material balance. There is an integral function to smooth out data. It makes it easier to interpret. In numerical RTA, there is a way to use cumulative LFPs instead of instantaneous. It's the same thing. Exactly the same thing as. Any questions, or was this straightforward? Yeah, about the derivations on slide 64. Yeah, if you like to derive them, that's a very useful exercise. Maybe I have some notes when I did it myself here, but it's pretty straightforward. Okay, so we've done classical RTA again. The essence is the contact to pore volume and the LFP. That's what RTA is about. So we're going to increase the difficulty level a little bit, and we're going to talk about RTA, numerical RTA, for the second time. We talked about classical RTA 2 times now. And that's going to be 2 times. Numerical RTA, we're going to talk about it 2 times, and this is the second time. We mentioned already that the inputs, that PVT, is production data, and it's rel-perms. Rel-perms is something that we're going to change it for a few of the cases that we work on. Typically, I see that a lot of people, they are successful using a very similar rel-perm set for a lot of wells in the same area, so that's important. But a little bit more deep dive on numerical RTA. So just like with analytical RTA, we assume the same type of geometry. So it's a one-dimensional model, and there's no flow boundary beyond the frac, or there's no flow beyond the frac tip or frac. It was introduced by Braden in this paper in 2020 to solve some issues with classical RTA. And classical RTA had, in 2020, had been the industry standard workflow for 20 plus years. And the issues that we're trying to solve is what I'm going to try to explain here. The square root of time plot works extremely well when you're dealing with constant. So this is constant pressure above the bubble point. So that's single phase flow above at constant pressure. So the simplest thing. So what the square root of time plot gives you then is that as long as you're infinite acting, you should see a straight line on this plot. And if you're seeing any boundary effects, you just start to bend upwards like this. So far, so good. And the slope here is what gives you the LFP. That's what we talked. If I go in here and I say, let's keep it single phase, but I just introduce a little bit of superposition, for instance. If I go in and introduce a little bit of superposition, the problem that you'll run into is that now you'll start to see a wide range of transients. So every time you change your bottom hole pressure rapidly, you now get as many slopes, potential slopes that you'll see here. So this is the same data. The well is still infinite acting. Okay, that's important for you guys to know. The well is still infinite acting, but it's impossible now to interpret this plot to the right. So the only difference that we've done is instead of using a constant bottom hole pressure, we're not even doing multi-phase here. There's no multi-phase. There's just changing of pressure. So it can be really tricky if you have a lot of changing in your bottom hole pressure. And then if we introduce one more complexity here, let's say we go below the saturation pressure. Here is the same well. This well should always be infinite acting. So on the square root of time plot, it should give us a straight line for the whole period if the theory was kind of going coherent. If we take this exact model, the reason why I know it's infinite acting, by the way, is that it's my model. I made it. So you can check that numerically if the model is infinite acting. And we know it's not. Or we know that it is for the whole period of time. So here I just plotted the bottom of pressure versus square root of time. And this is 2 examples where we go below the saturation pressure at 290 days. And we also go below the saturation pressure at 140 days. Same model, just with different drawdown strategies. And what you see if you superpose the square root of time plot is that there's a deviation just when you go below the saturation pressure. And that's happening when you go below the saturation pressure here and here, 2 different points in time, and you get basically these fake infinite acting periods or these fake time to end a linear flow kind of signals. That's what you're getting here as you go below saturation pressure. And this was what Apache and now a lot of other companies as well have identified in their own wells. So this was in the Midland Basin and the Permian. And what it would always lead to is, okay, we talked about this now. Classical RTA, the earlier I put that slope, then the smaller my contacted pore volume is, and the smaller my contacted pore volume is, the higher my permeability is, my shorter my fracture half length is, and the more wells I'm justifying per section, and you're overcapitalizing from it. So that was why this Bowie workflow was introduced a few years ago. It has nothing to do with the David Bowie or James Bowie or the Bowie knife, but it's just off the Braden Bowie at Apache. And that workflow is built upon three fundamental relationships. And that's actually if you read this paper, there's a lot of things in the paper, but the big finding in the paper is actually these three fundamental relationships, and that's very important. And I don't think it's been really put in any paper before that particular paper. So what those three fundamental relationships are telling you is, if you have two different wells and they have the same average K, then the rate performance is identical during infinite acting behavior. And if the ratio LFP to OIP is the same, then the relative ratios will be identical for all times, both infinite acting and boundary dominant. And the last one is if you have the exact same values of LFP and the contacted pore volume, the rate performance will be identical for all times, both infinite acting and boundary dominant. And this will be, and this is true if these two wells have the same PVT, rel per set, and flowing bottom hole pressure versus time. And you might be asking, Matthias, what two wells actually has these things the same? Well, none. But the key part here is that we're actually applying these three, or the knowledge of these three different relationships on one given well. Okay. So and one given well should have a PVT relationship, a rel perm relationship, and a bottom hole pressure history versus time that is more representative. And just to remind yourself that this is true, if you have the same infinite acting or the same LFP, the performance during infinite acting time is the same. And then we'll see this deviation late time. The deviation is related to the contacted pore volume. This is a large contacted pore volume, smaller, smallest. If the ratio of LFP to oil in place is the same, the relative rates are the same. So GOR and water cut will be the same. So here they're all overlapping. And the other thing that you can see is that the rates and cumes, they're just a perfect multiplier of each other. So if we scaled them to the same LFP and oil in place, then we'll get exactly the same well performance history versus time. And these are the fundamental building blocks of what is called the numerical RTA workflow, or the Bowie workflow. And when you click, all of this is automated in modern call it RTA softwares. But if you would like to know what's going on behind the scenes, that's what I'm going to essentially teach you now. And we talked about material balance time earlier. I think the reason why material balance time became really, really popular is that it's very easy. Everybody here can do it in Excel. Square root of time plot is the same thing. And the same thing goes for the Bowie workflow too. As long as you have access to a numerical model, you can replicate the steps. So I know at least a dozen people that before this was involved in any softwares and stuff, they could do this in Excel, and the same goes for you. So I think that's one of the reasons as well. It's fairly easy to understand, and it's also very easy to implement in a spreadsheet. So if we start with step number one of the Bowie workflow, what is actually happening when you're clicking run in numerical RTA? And what is being done is that one huge model, like a numerical model, in terms of like size. So that means that we know that this will never hit boundary dominated flow in the whole historical time. We create a numerical model that's large enough to behave infinite acting for the entire historical time. How do you do that? Well, you do it through trial and error the first time you set it up, and then you can use that base case from there. You do it to make sure that there's a far distance to its closest boundary. Since I created this model, I know what the permeability is, I know what the XF is, I know what the height is. So I also then know what the LFP of this model is. It is an arbitrary LFP. The only thing I need to do is make sure that the distance to the closest boundary is given. The second step is that I take the actual bottom hole pressure that's measured in the field, and I control the model on that measured bottom pressure, or if it's calculated from a calculation. And with that information, I get, 3 different rates: oil, gas, and water. And the oil, gas, and water rates, they will essentially have a flow regime that has been enforced upon them. And that flow regime is infinite acting flow. So this is how it would look like if the well was in perfect infinite acting flow. So step 3 is that you calculate the ratio between the actual production data and this infinite acting model. And that ratio over time just represents how many of these infinite acting numerical models would I need to match my actual production data over time. And this is where you could do this in 2 different ways. You could use the actual rates, or you can use the cums. If you use the cums will be kind of equivalent to using integrals in either the RTA, classical RTA that we talked about, or in the MFMB exercises. Okay, so we get this ratio over time, and then the only last thing you do is that you take this ratio and you multiply it with whatever that LFP was in your initial model, that arbitrary LFP, and you get the diagnostic plot, this Bowie plot over time, where a flat horizontal line indicates infinite acting linear flow, deviation below this line represents boundary dominated or transitional flow, and the magnitude of the flat line itself indicates the LFP. And then the only thing that you do is that you repeat these steps for a wide range of tank sizes, and those tank sizes have a varying degree of tank sizes, such that if they get smaller and smaller and smaller, they will go into boundary dominated flow sooner and sooner and sooner. So this would be the infinite acting case, and then you make it smaller, 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 and you'll see deviation from that straight line happening sooner and sooner. And then, when you go in and pick the LFP, you look at the LFP from the data itself, you overlay these type curves, and you pick the closest OIP step. So if you did this on like real data, it will look a little bit noisy. Maybe something like this. Flat horizontal line indicates infinite acting linear flow. Deviation below the line represents boundary dominated flow, and the magnitude of the flat line itself indicates the LFP. And then, when you have these different type curves, you pick the type curve that's closest to observed data. And what have you done? You've done RTA. You picked A/K, and you picked contacted protocol. And this is kind of the 4th part of this unconventional reservoir workflow, where you have already made an assumption of PVT and rel perms. You've done your interpretation, your RTA interpretation, and then if you want to, you can use that to resolve physical parameters such as XF and K, and that's what you will bring into a numerical model. And the beautiful thing here is that numerical model will have a perfect history match, or at least as a good match as you've done your RTA on the first run. That's a great thing. The second thing is, you remember when we talked about classical RTA? You have to, pick material balance time. You can pick some of these other time functions. Everything here is in real time. So everything is like in the real time where we all live and work and breathe and whatnot. So that's another benefit of it. And the third thing is that it also accounts for this combination of superposition and multi-phase flow effects. But what are the downsides? Well, classical RTA is instant. It's like super fast. And the downside of numerical RTA is that it takes a little bit of time to run the model. Might be 10 seconds or so, depending on how large a data set is. And then you might have to make sure that you have homed in on reasonable geomechanical parameters and also rel perms before you do the workflow. And just a reminder, if you've done a lot of classical RTA stuff in the past, the reminder here is that the A/K, that's your LFP, and time channel linear flow, that's your contacted protocol. So it's exactly the same things if you've always done. You're just using a numerical model. The absolute last thing we're going to do, or actually there's a few other things, but maybe before we're going to take a break again, is to in detail talk about fractional RTA. And I think we defined a problem earlier. And again, we repeat a few of these things a couple of times. Problem is that all the classical RTA models, they assume equally spaced fractures, while in reality, they're more complicated. Might look something like this or something like this. So in a nutshell, the difference was that classical RTA solves for equally spaced fracture networks, while fractional RTA solves for more complex systems. And the LFP was slightly different, and we also learned that we could quantify the rate or this delta parameter from using rate normalized pressure versus time. We're going to do this together a little bit later, where you can do that using this plot, or you could actually use the inverse plot as well. And what does this delta mean? Delta of 0.5, that's infinite acting linear flow. Boundary dominated flow is delta of 0. And transitional flow is a delta value in between. So if we take a look at this equation, this is the equation. And this is gonna scare you guys if you, at least I still have nightmares from calculus back in school. So if you're in the same boat, then you might probably want to close your eyes when I show these equations. But this is the solution for n when you look at this equation here to the left. Okay, this is for oil and this is for gas. But it looks difficult at first, but you'll actually see that it's familiar. Because when delta, if you plug this into Excel, if your delta is equal to 0.5, then this becomes 19.927. And we've seen this before, and that's essentially this guy. And that's something we saw at an earlier slide. And the same goes for gas. If delta is 0.5, this becomes this solution right here that we also saw on an earlier slide. So we've all seen this before. A lot of people, if delta is something that is linked to, let's say, complexity. A little challenge that I have for you guys, and that I've seen a lot of clients try to do as well. Try to correlate delta to completion practices. If you have a delta around 0.5, it should mean that you have very high cluster efficiency because the distance between the fractures should be similar by, if you go from 0.5 to 0. Well, if you have a really, delta that's very complicated and you see a lot of delta progression and changes over time, it might indicate that your cluster efficiency is something else. So that's maybe a little homework for some of you guys if you're interested in trying to tie some of this stuff to completion practices. I'm also going to do a quick section here. That's not something we're going to do in the software because it's not something we have in the software yet, but it's hopefully coming over the summer. And that's where we are basically combining fractional RTA and numerical RTA. So just it's pretty simple. We presented a paper a couple of years on this, and it tries to solve some limitations of classical RTA. Where if we're really seeing something that was in true transitional flow for a period of time, you'll see that your stems will cross through a wide range of, or your actual data will cross through a wide range of stems in reality. We also know that this can be modeled with geomechanical effects, and of course, is it actually complexity or is it geomechanical effects? It can be a little bit hard to say off the bat. But at least a way to combine these two technologies is what I'm going to show, at least the theory of right here, where, in that world, LFP is defined as basically a k to the delta. The pore volume is still defined as the same thing. And these fundamental relationships that we talked about in numerical RTA, where you have A root k, contact to pore volume, and delta, those will be identical. If these are identical for a well, then the rate performance will be identical for all times, which means that you'll have the same production during infinite acting, transitional flow, and boundary dominated flow. So that's the fundamental relationships. An example of that, this is 3 different cases where all these, very different, porosities, very different well lateral length, etc. But as long as these parameters are the same, then case 1, 2, and 3, they're perfectly overlapping. It looks like it's only one case, but it's exactly the same results. Okay, so it has a lot of similarities in that sense. And the way you would model delta, and that's one of the genius paper from Hori Akuna in 2020. He basically provides you a recipe that if your delta is 0.3, it just tells you, okay, then you need a distribution of different symmetry of element models that all has a different size. Let's say 60 of this, 10 of this, 15 of this, etc. Comes straight out of that algorithm, and that he has presented in the paper. We also have that in our manual, that's how you would essentially model that type of complexity. And then, even though each and every one of these symmetry of element models, they would have a period where their delta is 0.5, and then it will go to basically 0. So the individual delta of each of the models is 0.5, but when you combine them together, they're able to predict something that's not 0.5. And that's the whole kind of premise of doing this. When it comes to the workflow itself, it's exactly the same inputs, but in addition to production data, PVT, and rel perms, you now have this delta parameter as an input to the workflow. So that's that was a little bit of, I guess, foreshadowing a little bit on what's to come on that front. But it's going to be very elegant, very, the delta will be 0.5 by default. If you'd like to make it something else, you of course can. The absolute last part we're going to talk a little bit about before we're going to take a break, and then we're going to jump over to the exercises for those that would like to join those. Is we're going to talk about the simulation piece or the numerical piece. So numerical RTA and the numerical model, they use a numerical engine. And here's important for me to emphasize that when you are doing RTA, you're quantifying an A root K and you're quantifying a contacted pore volume, you can come up with an infinite number of realizations. So I can combine, here's just three different examples where the well lateral length, the number of fractures, the frac height, etc., your fracture half length, your permeability is very different. But as long as those parameters are the same, my numerical history match is exactly identical. The other thing is if I keep the abandonment pressure the same, also my forecast will be identical. I'll repeat that one more time. So like when you do RTA, you get your A root K and you contacted pore volume, and you can combine those parameters in an infinite number of ways to come up with a history match. And that history match will be the same no matter how you decompose those different parameters. So it's very easy here to get tricked into believing a mental model that you already decided on, because you have actually given the model a lot of the inputs, right? So, but here I can say I can come up with an infinite number of other possibilities that just from the RTA work, will give you the same results when it comes to fracture half length, etc. So that's why when you do this type of work, when you're call it resolving reservoir parameters from RTA, you need to feel good about your metric porosity. You need to feel good about your fracture height. You need to feel good about your well length. Obviously, it's probably easy to feel good about, and you need to feel good about your number of fractures. And also remind yourself that you're making an assumption that your geometry is the perfect rectangle. These results, they should be the same in any physical engine that you're running, as long as those are full physics. And every time you run a physical engine, like the one we have in Whitson Plus, there's something called grid refinement. And before you run the model, there will be an option to run the grid refinement, very low, medium, and high. And that grid refinement we have in Whitson, at least for these models, it's a mix of both logarithmic and Cartesian gridding. So we have basically a uniform gridding within the frac tip right here. In the main direction of flow, it's logarithmic gridding, and beyond the frac tip, we also have a log gridding. And the reason why numerical gridding is important is because there's something called numerical dispersion. And numerical dispersion just causes the results to be less accurate. So if you have very coarse grid cells, like why can't we just use one grid cell type of thing? The reason why you can't do that is because the results will become numerically not so accurate. So we say that the model has not numerically converged. So the problem is that when simulation grids are coarse, the numerical dispersion is this undesirable simulation artifact. So the sufficient gridding is then required to make sure we actually get reasonable results, but also it slows down runtime. So in reality, it becomes this balance between accuracy and practicability. So many times I see, like, if you do a history matching exercise, numerical RTA, people like to run it on low, and then maybe in that final run where they would like to present, put in a presentation, etc., they put in a little bit more level on their gridding, for instance. Low in Whitson though should be pretty decent at the from the get-go. So it should be in really good shape on that. But there's cases where there might be justification to increase the grids to like medium or even high S. The second thing that you'll pick on the top there is the well control. That just means for the numerical model, numerical RTA will always control it on BHP. But when you're in the numerical model, you can actually control it on oil, gas, water, BHP, etc. So you can pick yourself what you like to control it on. So if you control it on oil rate, it means that the oil rate will be matched perfectly. And then we're trying to solve for all the other fluids. Similarly, on gas, we do the same thing. We solve for pressure, we solve for oil, and we solve for water. Water it's possible, but it's not very common to use because typically we're not injecting the flowback water. And then the problem with bottom of pressure sometimes, at least if you haven't smoothed the bottom of pressure, is that you can get pretty spiky rates. And if, typically that comes from the fact that like a true bottom hole pressure is actually really smooth if you've seen one in reality. So any type of very abrupt changes of your bottom hole pressure can really create your predicted oil rates to be kind of spiky like this. The last thing just to remember here is, okay, when we have a numerical model, we have our RTA interpretation, and we want to make a forecast. But there's two types of forecasters. We have those who don't know, and those who don't know they don't know. What I mean by that is, from the end of history here and out, you need to make some assumptions of, what would you like your abandonment pressure to be? Should be high, low, should be 500, should be 700 psi, whatever it should be at the end of history. And that piece is something that is kind of an unknown. Maybe you have some analog wells, maybe you have some good reasons based on surface constraint or the depth of the well, those kind of things. But just make sure that here that it's probably better to be consistent than everything else. And this is when you append the forecast, and that's just an example of that. Perfect. At this point, we'll take a 15-minute break. We'll be back at 10:15. And then if there's any, maybe there was a question here.
There was a question from Jack to Matthias. Yeah, just wanted to wait.
Perfect. So the question is about delta for different completion, plug and perf versus like the NCS style type of completion. So if you have, the NCS style type of completion, there that every single fracture that you made has been initiated. So then you kind of know the fracture count with much more, confidence that compared to your plug and perf cases. So that would be like for the NCS, I think the delta would be much cleaner than if you did plug and perf, for instance.
Yeah, those who don't have access to the software, I'll just put the information about the software access in the chat. You can log in, so you're ready for the exercise now when Matthias comes back.
Okie dokie. So we'll get started again. Mo, can you hear me okay? Or
yes, sir.
Perfect. I don't know, for some reason the muting thing doesn't work, but that should.
I think your camera is not on, but I can hear, or I don't see the camera.
Yeah, my Teams is acting up a little bit, but as long as people can see the screen, you can see the software now, right?
Yeah, see the software now. You're on the Matthias Carson RTA course, and you're moving your mouse.
So what we're going to do, we're going to take some good times for these exercises, and we're going to reference some of the material that we've talked about and learned, and we're going to focus on these two features here, and then do a little bit also in the numerical model piece. And the first well that we're going to do work on is this well called this guy right here. And if you would like to follow the exercises, make sure that you click this pheasant well.
Matthias, you got muted now.
Okay, that's interesting.
Yeah, now you're good.
And these geomechanical parameters, let's make these two. I'm going to show that one more time. Once we're in the wells, I'm going to go to pheasant. I'm going to make these two parameters here too. These are just geomechanical parameters. A lot of people use 2 as their defaults. Okay. I'll make sure I go slow. Once we're happy with that, we're going to go to PVT here, and we just need to make sure we have some PVT properties. So here, there's a reservoir fluid composition card. There's a little edit icon here, and that edit icon, we're going to click it. Again, I'm going to show all the way up to this guy. You go to method. You change that method to dry or wet. That's what we're going to do. We're going to put in a specific gravity of 0.6. Okay, and we're just going to keep the other one here 0. And these are just properties we need to get something going. And these wells have actually uploaded bottom hole pressure for us, so we're not going to do anything there. And this is a super boring type of PVT because it's a dry gas well. But we like to start with dry gas wells because they're simple. And once we've done that, I would like us to move all the way down to analytical RTA. But I'm going to give everybody, I'm just going to repeat the 2 first steps first. Go to pheasant, and then go to matrix gamma and fracture gamma, make these 2. Then in the PVT, we just change the method to dry wet gas, and then we make this 0.6. See, Dylan is working on the same well as me. I don't know.
Yeah, just show how to make sure that you're in the right project and in the right well and all that.
So I don't know if Dylan from Chevron, if he has a project, can you make sure that he gets a project, Mo?
Yeah, I'll fix it here.
Yeah. Okay. So the matrix gamma and fracture gamma is set 2. We've set the PVT, and if we go to production data, we see that our flowing bottom wall pressures. They're already uploaded for us, so we're going to use that. There's water and it's gas. This is an interesting RTA exercise because this well has actually been choked back for a long period of time. But it's basically been producing at constant rate for a long period of time. And that's probably in a scenario where it's even more important to do RTA. Once we're done here, we don't have to do any of the stuff above, and that's for another course. If we went in-house and we did the whole Whitson plus kind of starting course, we will go through all of these. But we're going to focus on these two guys today, analytical and numerical RTA. So we're going to go to analytical RTA, and we're going to open up this interface. And I'm going to, if you guys don't know this trick, it's a helpful trick where you can do function F11 or just F11, and it just maximizes the whole screen in general. If you like to do that, you can do that. And here I'm going to go very slowly through all the moving pieces on this page because it has a lot of the things that we talked about and that we just learned, the theory piece. And again, this is the classical RTA piece. So in the RTA here, you have classical up here, and then fractional here. At this point, I want to make sure that you have done some of the basics. Make sure that your zoom, depending on the screen size, that your zoom is probably put to 80 or 70%, depending on how big your zoom screen is. Your screen should probably look something similar to my screen. If you've zoomed in too much, it might start to look weird, like this. Make sure that you have something that looks like this. And again, we covered three things already twice: classical RTA, numerical RTA, and fractional RTA. And this is the classical RTA piece. So I'm going to start here up to the left where there's two buttons. The calculate button just calculates these guys. So it is actually activated by default for us. This is nothing to really worry about. This autofit guy, though, if you click that, what the autofit will go in and do is that it will do an automatic fit of our square root of time plot data. Okay, so the machine or Whitson Plus will go in and interpret what is, quote unquote, linear flow, and where should I fit my time to linear flow. That's what the autofit is doing up there. And below this, we have a couple of different options. The one is the time function. The default is material balance time. And the reason why the material balance time is the default is because what we talked about with the consistency of these analytical equations and converting stuff to constant rate space. And we're going to change these later. But for now, keep it material balance time. The other thing here is we have different phases. This we're going to talk more about when we deal with some of the other wells. This is a dry gas well, so it's not that interesting, but that's up here. And then below here, that's where we start to get some of the key interpretations. And this is where it's going to start to become a little bit important, but I'm going to just walk through each of these. So this guy is your A root K. So that's one parameter, and we'll see how that interacts with the plot a little bit later. This is your time to linear flow, and this is the size tank, and this is something we call drainage area, and that is a function of your XF, what your fracture half length is. So this will be calculated automatically. That's a surface area, and then these are the assumptions. So this is a well from SPE. This has been an assumption that's been provided to us by the SPE. This is the porosity, this is the fracture fracture height, number of fractures, well lateral length, and these are some of these resolved parameters. This is the water saturation, rock compressibility, initial reservoir pressure, and in this case we've solved for K and XF. You could also solve for XF and NF if you wanted to do that over here. At the bottom is what we call empirical assumptions. And those empirical assumptions is just, okay, if you would like to fit some kind of B factor at the end, like after this time to linear flow over here, that it will be coming from whatever this B factor is. Okay, so you can change this to 0.8, for instance, and that will have an impact on this guy right here. Okay, and by default, that will be default. The main RTA pieces, the main things people are using RTA for, first, calculate these rate normalized pressures and pressure normalized rates, getting an A root K and a contacted pore volume, and this time to linear flow number up. That's some of the key things they're using classical RTA for. So this is what we have to the left here. Then we're going to go through each of these plots and what they are. And I'm actually going to start with this pressure normalized rate plot. And all of these plots, they have an option up to the right where you can expand the plot. If I click expand here, the plot will take most of the screen like this, so that I have more real estate to work with. And here I'm also happy with my zoom on the screen. So if I'm happy with my zoom, I can click this lock zoom button, and this lock zoom button will allow me to not alter my zoom when I'm adding slopes and whatnot. So when I lock the zoom, I won't be able to change the axes. I will have to unlock the zoom to change the axis. And I think this is a good place to just take a quick stop for that. At least I know some of you guys live in Whitson Plus, and some of you probably have never opened it. So it's a good mix there. But just if you haven't really used the software that much, if this is unlocked and you want to zoom the axes here, the way it works is that you need, if you want to change this, for instance, you need to be somewhere above the middle until your symbol have changed to this vertical line that goes up and down like this. And then I can essentially drag and drop. If I'm lower than the middle, I can do the same here. The same goes here. If I wanted to type in the numbers themselves, if I would like to make this number here something else, let's say I would like it to maybe like 15,000 instead of 10,000, I can just type in the number. Same goes here. If I want to make this 2 instead of 1, I just click it one time and I make it 2, and it shows up like this. Okay. So as long as you're seeing this symbol right here, you can click one time and you can make this number whatever you want, and you can click enter. So the most important thing of the zooming. If you have zoomed yourself out of control, which happens regularly to myself too, there's a reset zoom up to the right that you can click. That will reset it like this. And also related to the zoom, let's say I was super interested in some parts of the data here. I could go in and say, just click and hover over that rectangle, and it will zoom into that part of the data. And now I can click reset zoom, or I can double click the plot of it, or I plot that. Yeah, there we go. Okay. So I think that's covering the most. If you want to change the axis, you just make sure you drag and drop like this, or you click one time and you can change the number yourself. If you like to zoom in, you hover over the data you like, and you select that. If you're happy with your zoom, you don't want to change it, you can lock the zoom so that it doesn't change. And especially before you start to work with slopes, that can be helpful, because what happens sometimes if I want to add a half slope to this data, now I can actually change the slope. Now I cannot change the slope. Okay. So now I can change the slope. Now I can't. What's a little bit annoying, what happens sometimes if this thing is not locked, I start to drag the slope here, it will start to zoom, and I'm like, hate when that happens. So it's much better if if you want to be bulletproof on that, so that doesn't happen, that you lock the zoom there if you want to. A half slope on this plot indicates quarter slope, indicates bilinear flow. It doesn't really look like that here, but it looks like something like a half slope initially. And then at the end of it, you can add a unit slope to see if you're in boundary dominant flow. And it looks maybe late time here that we've entered boundary dominant flow. And these slopes can be turned on and off as you like. Here, I don't know if the slope for quarter slope makes a lot of sense. And once you have these slopes on here, I can turn off the legend here at the top. Maybe you can also turn it off here if you want to. Here we've talked about flow regimes, and we talked about that you need to have an opinion on what you think what flow regime this well is in. So now with the things that you learned, like half slope is infinite linear flow, unit slope is essentially boundary dominated flow. You can make up your own mind what you think, at least looking at this diagnostic plot, what you think the flow regime is for this particular well at the end of history here. And again, if you click this expand, you can click the collapse button here. Again, here we haven't done anything. The only thing we've done is to look at a diagnostic plot. So this is this first bucket. We haven't done anything else than adding some slopes to the plot here to see what are we actually looking at in terms of slopes. With this, the theory says that as long as you're on a half slope here, that's where you should basically fit this straight line. And what can be a little bit tricky sometimes is this is square root time and this is real time. And that's where it's very helpful to have this time to linear flow line here. So you actually see, okay, this is when it starts to deviate from a half slope to to something that's lower than a half slope. So that's a nice cue scheme. Now we're going to take a look at this plot up here to the right, the square root of time plot. That's where we start to quantify numbers. It has a lot of the same functionality like down here. Has the lock, has a few other things that is if you want to filter data and lasso fit data and stuff like this, some fancy type of functionality. But for starters, I would like to focus on the LFP and its relationship to the slope. So, this is around 500,000. So let's say I make this 250. You don't have to do this, but let's say I did it. What do you think will happen with the slope? Will it go up or will it go down? A tab out. Well, we saw the LFP was going down, so the slope needs to be steeper. And vice versa, if I made this a million, one more there, it gets steeper. The LFP here is basically where I pick what my, or the slope is where I get my A root K and vice versa, okay? Because we saw from the equations we looked at that A root K is just a combination, or like the slope is just a combination of PVT properties and your A root K. That's where that comes from, okay? And I think the autofit has probably done a much better job than I, so I'm just gonna do that again. Similarly, this time to end the linear flow, if I made that, if I made that 100, looks what's gonna happen with my OGIP. Well, made it 100, it went down. And when I start to move this guy to the right, you'll see that the OGIP is increasing, the contacted OGIP. My LFP is the same, but now the time to end a linear flow is increasing or decreasing my OGIP. Okay, so that's the contacted oil or gas in place in this case. And yeah, and also pay attention that everywhere in the software where we're mentioning or referring to the volume result from an MFMB method, or an FMB method, or an RTA method, we're referencing the contacted OGIP. That's on purpose. So far so good. Slope A root K. This is our pore volume. Okay, so now we're basically kind of in bucket number 3. And then we'll later also show how we can make some simple diagnostic plots. When we're at this page, I want to show a couple of things. This button right here, you can click and it gives us the integral and it smooths out the data, but all the interpretations stay the same. So that's implemented in a consistent way. So you should get really similar answers. So that could be a nice way to cross-check your answers. And then you have this option called plot derivatives, which is here as well. And you'll note that when you've added the derivatives or you've done the integral, that will happen in both of these plots. Except from that, there's a few other options up here that I'd like to talk about. Sometimes if the intercept, if we pretend that the data was higher than 0, that means that you don't have an infinite fracture connectivity, or that you have some kind of positive or some kind of skin. So some people, they like to basically on older wells, when they do this interpretation, lock their intercept to origin, which means if I click this button, this part of the slope will always be locked, and then I can move the slope around as I want, okay? And that just basically says we think that the fractures are infinite conductive, and that's the assumption we want to make, and that's how we want to pick A root Ks consistently for our wells, okay? So that's this option up here, and you can untoggle that if you like. If I move this slope for some reason, if this slope disappeared outside of the screen, and that's in every single slope that has, or a plot that has a slope on it in Whitson, there's a reset. That reset will basically bring the slope back. Also here, if you see now my slope is in the screen, but I can't pick the ends of the slope. So if you click reset, it will bring it back in here between these two guys. Good. I think that was kind of the moving pieces on the plot. Maybe you guys have a different opinion than the autofit, that instead of this LFP and this contacted pore volume. But a lot of people like just to let the autofit pick it as well. And right now, what we're going to do is we're going to talk a little bit about these other time functions. The time functions are real time and linear superposition time. And when I talk about these, I like to bring this article up, and it's just referencing a few things related to classical RTA models. So when you do classical RTA, we need to pick a time function. And the industry standard is to start with material balance time. A lot of people like to look at it in real time as well, or other people like to use what you call linear superposition time, which is this option right here. And I want to spend a little bit of time talking about these different time functions, and just warning you a little bit that once you're applying a time function, you have already biased your interpretation. And it sounds a little bit recursive, because you have when you want to use classical RTA to identify your flow regimes, But here Matthias is saying that you've already biased your interpretation if you picked any of these time functions. So what I'm referring to, and this comes out of a famous Louis Matar paper, but it's true in general. And it's something we mentioned in this particular article, that the superposition time functions used will always bias your interpretation. In many situations, using the square root of time superposition, which is the linear superposition time, makes the data look like linear flow, while using log time makes it look like radial flow, and using material balance time makes it look like it's in boundary dominated flow. So that's why a lot of people here, they like to use real time before they make up an opinion on what their flow regime is. And they also like to wait until they've finalized numerical RTA before they make a really confident decision on what they think their flow regime is truly in. Because in this case, real time, there is no superposition, but just using real time has its issues. Material balance time will take all the bad data and put them on a unit slope, while linear time, you see it here, then you're assuming that you're in linear flow, so it looks much more linear. So it looks like we're in linear flow the whole time. So all this data, just because I changed the superposition time function, moved from this unit slope up to this half slope. I think everybody sees that. And that's something that I think is a little bit under communicated, and it's just something I wanted you guys to be aware of. And there's more information about that in that article, and I can send that article in the chat for those that are interested in that piece. Okay, so I talked a little bit about time functions. The reason why we use material balance time is that when we use material balance time, these equations right here, they become rigorous, or as rigorous as they can be. But no matter what we do here, these are still analytical equations, and they don't rigorously account for the combination of PVT and superposition. And even, a question that might come from the audience is like, Matthias, this well is a dry gas well, produces a little bit of water, and else it's dry gas. Like there shouldn't be any multi-phase effects here. That's a great question, and I'm glad that was asked. But the problem is, okay, even if you're not multi-phase, here you're assuming constant PVT properties. Okay. I'm going to repeat that. So if you remember, when you use these classical equations that we learned about in the course, when we went through these classical, so these equations right here, they're assuming PVT properties, but these PVT properties are at initial reservoir conditions, and that's not rigorous. So even for a dry gas well, it will introduce problems using these analytical equations. So that's why we're going to move into numerical RTA to deal with these items. Any questions here? Clear, or at least clear as mud? Maybe I'll just let's do. Okay, we're good. Just before we leave this, I just wanted to. I'll probably share this also, maybe as a follow-up, but. We wrote a little paper for UTEC Argentina last year about this for dry gas wells, and it has this really nice reference to Augerwell's paper in 1979, where this problem about, and this was for well testing, but it's the same thing for RTA. Like we use the PVT properties at initial reservoir conditions. So he basically mentions that it is not clear as to which pressure level the viscosity multiplied by compressibility product in the dimensionless term should be evaluated. The question arises whether this term should be evaluated at the initial reservoir pressure, the final flowing bottom pressure prior to shut-in, or some average pressure of the two. The results of the study indicate that the use of these any of these three pressures are less than satisfactory. And that was why Augerwell, he introduced a concept called pseudo-time back then to analytically be able to work with this with this analytical equation. And it's the same thing here. Here we're going from 4,200 down to 12,000 psi. I can guarantee you that any of the PVT properties here, viscosity, compressibility, any of these will be the same for a gas system. So using PVT properties at initial reservoir conditions is not correct. That's just a given, and that's something that will be solved for with numerical RTA. That said, though, you can still use these properties for well-to-well comparisons. You can put them on the same diagnostic plot. There's still a value to be derived there, but it's just, if you want to, I guess, rely and trust on the interpretation numbers, at least myself, I would always go and use the numerical RTA results as my gold standard for that, because there I knew that's been at least or as few assumptions made as possible. And we got the question as well here on the RMP plot. Is the A root K the slope or the inverse of the slope? And that's a great point. It's the inverse of the slope. So I say it's the slope, but it's just meaning that it comes from the slope. But we see that from both both equations here, that LFP is basically 1 over this number, and then we also see it here when I change this to something steeper. If it was proportional, this should go up, but it goes down. So it's inversely proportional to this guy. And here, maybe some of you are a little bit confused with the units, and that's because for gas systems, it's something that's called pseudo pressure that's used. And that's relevant for gas systems at lower pressures. Gas systems at higher reservoir pressures, they behave liquid-like. So if you're 10,000, 12, 11,000, at least in the first few days, you can actually just use the same as for liquid. But later time, you would need to use the pseudo pressure relationship. Very good. So with that, we're going to go to numerical RTA, and we're just going to click run here up to the left. That's this button here, and then I know now we have a lot of people in the course, and I saw also a lot of projects here. So if it takes a little bit of time to generate this, it's just because there's a lot of activity on the domain, I guess. But here we're also going to spend a lot of time, and I'm going to convince you that it's the same thing as we've been doing in analytical RTA. That's my goal of this section right here. We're not in a hurry at all, and I would like you to hopefully at the end of this see that it's not as hard. At least if any RTA guys out there is selling it as hard, it's they're trying to fool you guys. So hopefully they're not doing that. Hopefully you're seeing something similar to me. If not, ensure that your gamma parameter here is 2 and this gamma parameter here is 2 in field units. So hopefully you're doing it in, even though I come from Norway, like I don't even understand anything that's not field units anymore. So it's good. Hopefully you guys see something like this on the screen. And I'm going to start to just go through this a little bit in the same manner as we did with analytical RTA and show you that it's very similar up here. The run button is just where you generate this Bowie diagnostic plot. And the reason why you have to run something, there's a question related to these gamma parameters. What do they physically represent? An excellent question. So let me just cover that. And that's just something you can add. So I'm in the manual right now, and you can actually see it multiple places in the manual. And I think it's the same everywhere. But these gamma parameters, they're just geomechanical effects that you can introduce, which means that you'll create or introduce a pressure-dependent permeability relationship, such that when the pressure is changing, your permeability is changing as well. So that's the most common way of modeling this, is to use this equation right here. Can't remember exactly what his name is, the guy with this equation, and the way it looks like, if you want to plot it, it looks something like this when you have a gamma of 2. And you can actually set a different one in the matrix and the fracture. The reason why I'm using 2, no particular reason for it, is just it seems to be the default with a lot of clients that I'm working with in Marcellus, and this is Marcellus well, I think. Good. And we're in this case, we're going to ignore the water. Everybody sees here. Yeah, exactly, Dylan. Excellent question. So a higher gamma means that the perm is more dependent on pressure. Yeah. So if the gamma was 0, it will be actually we can plot it. So if I made gamma 0, you guys don't do it. I'm going to mess up your work. But if your gamma is 0, the permeability multiplier is the same. It's 1 at any pressure. So it doesn't change with pressure. That's an excellent clarification.
I think you can also open gamma dialog Matthias, and then just change it live there, and then you'll see the effect on the number there.
Yeah.
Just make it 3, make it 4, and so you'll see that as you go make it 0, then it will be So you see the effect of what it actually is making to your pressure. Yeah. To your permeability with pressure.
So hopefully everybody's seeing this on the screen. If not, contact Mo on support if you are seeing something different. But you'll see that the layout is very similar. Next to the run, there's like an autofit button. That autofit button will use these weight factors right here. So if you click autofit now, like your autofit would make sense because the weight factors is like it's only weighting oil and there's no oil for this guy. So you would have to weight it to 1 for cume gas if you use this. But you can also just manually change these numbers. The thing here, the reason why you need to run something is that we're actually running a wide range of numerical models. So, we're 45 people on the call. So if 40 people run, this at the same time, it will be, hundreds of simulation models. And these are full physics simulation models equivalent to Eclipse, CMG, IMX, etc. That's being run on the cloud. And that's why you have to set a grid refinement. And you also can pick these number of type curves. And this just means how many of these different tank sizes would you like to be displayed on your screen. And for a few of the later cases, we're going to go in and actually change this number to 10. The phase here, the phase is not as relevant because it is gas. We're going to talk about that more later. But we have the exact same outputs that we have in the other classical RTA, A K, and it's a tank size. The A K is something that's related to the slope. So when I move the slope up or the line up, my A K is changing. You can also type in a number here and my A K is changing. And the OGIP will automatically be picked to the stem that's closest to my end of history right here. And we're going to talk more about the interpretation later. Else than that, we get the contacted pore volume. We can do exactly the same thing that we did in classical RTA, where we resolve a K and XF. And these are just the fluid inputs. And at the bottom here, we also see that we have relative permeabilities as an input as well. So here we're like rigorously accounting for rel perms, PVT, all the phases. There's 2 phases in this case. But we're gonna change these relative permeabilities for the other wells. And here everybody sees that we're not matching water. So I'm not going to spend any time on water for this well. We're going to spend more time on that for the other wells. But one step at the top of the screen here, in the main diagnostic plot, you'll see that the diagnostic plot has use cumulatives already picked for it. Same thing goes here. If you click these and you untoggle these, you're basically getting the rate versus time and the instantaneous LFP versus time. So back to the theory of RTA, the step 3 in the workflow, the difference between instantaneous cumulatives is just, are we using the rate that day or are we using the ratio of cumes? And the ratio of cumes is the equivalent of using the interval in analytical RTA. Okay, so if I did this, reduces the noise, it also reduces the signal. And if you untoggle these, you will see to the right that all these models, all of these interpretations, they have exactly the same LFP. The only difference between these are the size of the tank. And that goes back to this fundamental relationship that we talked about in the beginning of the course. Decrease my LFP, let's say, and I release it here. What will happen with my IPs? Well, all my IPs will go down. What if I increase them? If I increase my LFP, that's what I'm doing here. I'm changing up and down. My rates and IPs are going up. So far, so good. So far, so good. The other thing that you see is that the LFP in all these cases are the same, but what correlates with the long-term cumes is the size of the pore volume, the size of the tank. So the EOR, if I go here, you'll see this will have a larger EOR than this guy, and this guy, and this guy. And this is ordered in a direction of increasing cumes or increasing pore size, tank size. So that's also something that you'll see from here. At least to me, I get something close to 450 in my A/K, and I also get around 25 BCF in my pore volume. And we're not going to spend a lot of time on this next step, but if you click export here and you click yes and you click run, that's how you would run the numerical model. And that's maybe a topic for another course. Again, here we know our water rate is far off. But the beautiful thing now, and the reason why the water rate was far off was that we're not matching water here. So it's whatever we're matching in numerical RTA will then match very good here as well. Okay, so that's the beauty. And you could also go in here and export this, I think, to the numerical model. The problem when you do that with analytical models is that your fit will not be consistent and it won't be giving you a really good history match at the first go. So to sum up, like when it comes to numerical RTA, you're trying to find the piece of your production data here. So, here the actual production data is given to you in black, a flat horizontal line, that's infinite acting. And when it starts to curve down, that's when you see boundary dominated flow. And then you pick the closest observed stem here, which is around 25 BCF in this case, maybe a little bit on the low side. And you'll get a pretty good history match here too. Maybe the oil in place or gas in place could be even a little bit larger. And this number here, I could go in and override it. It doesn't have to be whatever the slope is here. So if I see, okay, here, I'm under predicting my cum a little bit. Maybe I like to make it a little bit larger, for instance. I could go in and say, I would like this to be 28 BCF, and I would like to lock it in. And when I lock it in, it doesn't matter how I'm changing these curves, because it's locked in here to the left. So it won't change my interpretation of my OGIP. Okay. And the same goes here. If I lock in LFP, I'm not able to move this line up and down. Perfect. So with that, we're going to take a quick break again. Okay, here the intercept in linear flow is useful potentially for early skin detection. Is there a way to interpret skin once the well is in boundary flow? Once you're in boundary flow, that's so just there was a good point here. The intercept is here is how you could interpret skin. So if there's a pressure drop between your matrix and the wellbore, you will have a positive intercept here. And that will basically be something you can observe in terms of the skin number or a not infinite fracture conductivity. And at least I have not seen anybody estimate that during boundary dominated flow. I've just seen how that's being done for linear flow. At least if you did this in conventional reservoirs, you would kind of have the assumption that you're in boundary dominated flow almost from day one type of thing. And those equations, radial flow and whatnot, they would have skin in them. But I don't think I've seen anything for unconventionals where you have kind of like the linear flow, and then you would have the boundary dominated piece with the skin in it, as far as I know. So the skin equation comes from the intercept. So if you look at skin and fracture conductivity, so that intercept on the y-axis, that's this B parameter right here, and it's just plugged directly into these equations that you see right here. Okay, and this is the equation where this intercept is the intercept that we were looking at here on the y-axis. We're good. We're going to take a 14-minute break, and we'll be back to do 2 more wells after the break, and that will be the course for today. So yeah, I'm going to stay muted in that period of time, and if there is any questions, just feel free to reach out. Okay, so I'm trying to get started with the last little session today, and hopefully if people are back, they could give a thumbs up, just make sure they're actually in front of their computer or something on the Teams thing. There we go. What we're going to do now is the two other wells. So it's going to be a little bit more fun, a little bit more maybe challenges, and I thought we could start with this well right here. Kite well, this is the one at the top here. If you click it, the first thing we're going to do is to provide some PVT properties. I want to show that again. Make sure that you're in your project, that you find the kite well, go to PVT, and in the PVT overview, we are actually going to just click save in this case. What we see now is something that's very different from what we saw in the other case where we were dealing with a dry gas well. So now we're dealing with something that's far away from the critical point. It's essentially, you see the whole face envelope for one, and we're far above the bubble point right here. So that's what we call a black oil system. You also see that on the GOR. We can also see that pretty easily here on the reservoir fluid type. Once we have our PVT, again, we're not going to focus on any of the flow material balance or like any of the bottom pressure calculations and stuff in this scenario. We're just going to assume that everything that we have been given is correct. So the only thing we will do here is just to look at the production data before we go into analytical RTA right here. Okay, so just to repeat, we have made sure that we have calculated PVT. We have made sure that we are also in the RTA module right here. Now we see again the default time function is material balance time. Phase is oil. It picks the primary phase automatically for us. Now we'll also look at a little bit of the fractional RTA stuff as well. On a similar note, the thing that's a little bit interesting here is that we could, for a multi-phase system, we can plot oil, gas, water, total hydrocarbon reservoir rates, total liquid rates, or total reservoir rates. That's oil, gas, and water. And if you change any of these plots, you'll see that your plots are updating accordingly. If you go to the user manual, let's say you wanted to look at the definition of all these different rates. What they are, they're just surface rates converted into reservoir barrels. So if you want to use some kind of other phase than the primary phase for your interpretations, then you could do that. And this is the way it's calculated. And it's just using flow and bottom pressure and PVT properties in that type of calculations. So all those equations are and methodologies provided here on the 1.3 cold phase. Else than that, we're dealing with a lot of the same stuff as earlier. I could go in and autofit this. One thing that's interesting when you look at the square root of time plot is you see there's a different color on the plot on the points here. And I could go and say, okay, I would like to remove the saturated numbers. And you can almost see here, if I remove my slope a little bit, then as soon as I go below the saturation pressure, my curve is starting to go upwards. So at this point, we would be, okay, is this actually a true boundary? Is it multi-phase effects? Is this something else? So that's why we have this toggle here to evaluate that, or at least at that point you should be suspicious or careful. What are we actually seeing for this particular well? Is it a true boundary, or is it just an artifact of superposition and multi-phase flow? The interpretations are pretty straightforward. I'm not going to spend too much time on it for at least this example, but if I went into fractional RTA, you could see that after cleanup, we're basically looking at a delta of 0.5. Then eventually we're looking at a delta of 0 that will be over here all the way to the backside. LFP around 60,000 looks like in this case. If I did my flow regime identification in my pressure normalized rate plot, we could see that this is a half slope and this is a unit slope late time here. But again, remember that I'm plotting everything in material balance time. So if I went and did linear superposition time, you'll see kind of the same thing going on, that it would drag out these data points in time. So just keep that in mind when you're looking at this, that boundary dominated flow or material balance time will make a lot of the bogus data points look like they're in boundary dominated flow. So I'm not going to make my final type of interpretation before I've gone into numerical RTA. But looking at these plots, it looked like, okay, we had a period of infinite linear flow, and then eventually I'm in boundary dominated flow. That's kind of my assumption, just looking at these diagnostic plots right here. And again, here I'm getting a content pore volume around 700,000 barrels. If I did this manually, if you wanted to look exactly at where it starts to change the slope here, I would probably pick something more like this if I did it kind of the classical way. In numerical RTA, the only thing we're going to do before we click run is just to change some rel-perm parameters. The only rel-perm parameter we're going to change, and this is just just to make sure that you build it into your fingers a little bit, that when you're dealing with multi-phase type of work, you're automatically in the rel-perm space. So in this case, we're just going to change this SWC from 30 to 10. That's a parameter that affects the water, so we'll produce a little bit more water. And then you'll just simply click run here up to the left. In the slide deck, in the appendix of the slide deck, there is like these cheat sheets on relative permeability. Those you'll also be able to find in the manual as well, but there are 2 cheat sheets on GOR and water cuts, like what parameters are changing these moving up or moving down. Okay, so you can also find them here in the software, where anywhere where we're talking about rel-perms, they're also in the manual. So again, here dealing with the same type of thing. We have different pore volumes. This line can be moved up and down to find a pore volume that looks better or worse. Here we're dealing with a cleanup period longer than the other one. That's also supported by the fallback period. Here we haven't injected any of that data into the model. So this looks like a pretty good fit where you put this at around 55 and you get almost 800,000 barrels in terms of your contacted pore volume. And we also know that if we bring this into my numerical model, my cum fit on oil will be really good. And the same thing goes up here for gas. So my contacted pore volume is 777 and my average K is around 55,000 in this case. And my stabilized water cuts are pretty decent. And up to the right here, you have a little QC thing where you can check what your LFPs and whatnot are from analytical RTA, numerical RTA, and compare it to the other parts of the workflow. So now I'm happy with my pick here. The last thing I'm going to do is to export into my numerical model. I'm going to click yes. Again, the nice thing here is that on the first run, I'll be able to get good results from my history match. So be very good on my hydrocarbons. It will be very good on so oil and gas. The delta here for water is just that in the beginning, I'm just trying to match the stabilized water. Pressure is really, really good. And if I wanted to, I can go in and append a forecast here. But I thought to show you, we didn't do that on the other well as well. So I just want to show that one more time. If you want to get the same results, make sure you pick something like this. If you hold in control and you click this stem, that's how you will only see one of the stems. And then you can click these guys on again. If you wanted by clicking, if you click one of these type curves, you see that the pore volume up here is changing. So if I'm changing it between these, they're actually changing. You'll see that as some kind of neat functionality. But this is the best pick, and that's picked automatically by the software. And it looks like here we're in boundary dominated flow at some point. It happens around 450 days or so. And if I compare the pore volume that at least I got from my analytical RTA, I get a larger pore volume in a numerical RTA, and that's in general what I'm seeing, at least for oil systems, condensate systems, near critical fluid systems and stuff. Typically, you will get a larger contacted pore volume when you account for a multi-phase flow and superposition. And again, everything here is in real time, so it's easier to interpret. And when you want to bring this into your numerical model, you click yes here, and then this will be your history match on the first run. And again, here I could, as long as the oil in place and gas in place here is the same, I could have changed whatever number of fractures that I want, the matrix permeability, well lateral length, frac height, you name it, to anything that I'd like to and still keep the same history match. So that's just a realization. So as long as these two parameters at the top here, average K and OGIP is the same, my history match will be identical to what you're seeing right here. And again, if you wanted to go from the numerical model from numerical RTA to the numerical model, you click export here, and that will export this parameter right here and this parameter right here. So a good question from Chris. Can you explain why you picked chose to put the straight line of the data where we actually put it? And that's a good question. So if it was a perfect example, this is the actual production data, this is the actual LFP, where the data is stabilizing, where that LFP is basically flat, that would be where you would pick your LFP. In this case, should it be here? Should it be up here? Should it be there? That's something that I'll leave up to the interpreter. What you end up doing much more when you're working with real data is, in addition to using the ski diagnostic plot here, you're also ending up using the cum plots much more as well, such that you do not only look at one particular stem, but you're looking at the diagnostic plot right here, but you're also cross-checking with the cum plots if they make sense. Yeah. Short answer, Chris, that was my interpretation of it. And I'm sure I've seen people who probably would say, okay, I think this is flat because it goes up here late time. And, maybe you're a little bit high here on the cums and whatnot in that period where you're not fitting it. But if that's your interpretation, I think some people would agree with that as well. And I'm not saying mine is right, but I'm just saying that was how I looked at it. Yeah. This is a great question from Tyler as well. There's a question about cluster efficiency. And I'll take a couple of minutes just on that. So, the number of fractures that we're assuming here, 306, should that be equal to the number of clusters, the number of stages? Should it be, some kind of cluster efficiency number assumed, or something else? And the reason why we, for instance, have two inputs here, like you can input the number of clusters and the number of fractures, and that they're not automatically the same, as a reason for it. In this case, we've just assumed that they are the same. That was what SB did. That would mean 100% cluster efficiency. I think among our clients, like close now to over 100 companies, I think I see primarily most people are using some kind of cluster efficiency, typically seeing numbers 70 to 80% of all the clusters. That's what I see. I'm not saying it's right, but that's what I'm empirically seeing from the clients that we work with. A little bit of problem we run into is like some clients, they like to put the number of fractures equal to the number of stages. Some folks like to put in more clusters than actual or more fractures than clusters, especially after these ConocoPhillips papers. And some people like to solve for a number of fractures, or they use some kind of cluster efficiency. But so I know, like, the answer was basically, whatever you like the most. I don't have a personal recommendation. I just say that we allow for all of it, and the most common is to use not 100% cluster efficiency, and typically a number between 70 to 80% of is what I see many people are using, but it can vary as well.
Yeah, I think just a quick comment there, Matthias, also that the beauty of numerical RTA is that you can solve the whole thing without worrying about these numbers being predetermined. So let's say you came in here and you change your mind about the number of fractures. Your analysis that you've done on the right side with the plot, with the biodiagnostic plot, with the LFP and the OIP that you picked would remain the same. All what's going to change is what comes out of that, which is on the left. It's the numbers, what matrix permeability and what fracture half length you would resolve. Maybe Matthias, you could show what happens here if you change the number of fractures.
Yeah, and I just want to reiterate that because that's so key, right? You can do all this RTA work, and if someone comes in and like, we want to change, for instance, our porosity assumptions or number of fracture assumption, you don't have to redo your RTA work. That's the beauty, because you have already made an interpretation of oil in place or gas in place and the A/K, and then you will just do this type of realization activity here. So in this case, this is 3 different realizations where these are the same and the history match is the same. And the same thing goes here, that if I locked these 2 guys in right here, keeping these the same, and let's say if I reduce the number of fractures, we learned that number of fractures and permeabilities is the same, the 2 sides of the same story. So if I reduce this to 200, I should see my matrix permeability go up. It'll end up to 15. And then same with fracture height. If I increase or decrease my fracture height, then my fracture half length will go up. And all these things I can change after the fact. And when I export it, I'll get exactly the same history match if I run it than what I had before. But now my realization numbers would be different, but the history match quality is the same. And that's, again, the RTA has been done once, and you can make all these changes as you like. Perfect. So for this guy, I know you guys have a little bit different numbers, but if you would like to add a forecast here, we just go to include forecast, edit forecast schedule, and then in the forecast schedule, you can just make this number 10,000 days. If you want to, you can reset the zoom just to see how it looks like. Click save, and then you can run it again, and you'll get that forecast for you. And remember that when we do RTA, flow material balance, that contacted pore volume that we're assuming here, that's everything that's stimulated, everything that we're able to get the flowing bottom pressure down to. So what we'll see is like, and this is a 100% material balance equation, this is counting. So you get recovery factors that are similar to what you have in conventional reservoirs from this contacted pore volume. But then, in reality, there's definitely some volume that probably isn't stimulated. So maybe your reservoir looks something that, more like this, where there's some unstimulated rock, etc. That's just not contacted rock. So that's an important clarification. And once you've, gotten your numerical forecast here, if you wanted to, in your DCA, yeah, you know, you can do an auto fit. I'm just going to do it for you. You don't have to do it. But if you have a forecast here that you would like to import, you can import that physical forecast as well from the numerical. We're going to do one last well. Yeah, I think, Jackie, for that, for open hole ball drop completion, I think I would assume all the fractures are contributing. So yeah, that's if I understand that question the right way. Should be really good science wells. Great. Okay, we're going to do the last well, and the last well I'm going to do. Yeah, I'm gonna show you guys a couple of things just real quick. So and don't do anything yet. Or let's just do the PVT together. For the PVT, let's just click save to make it run. We would pick that well right here, the crow well, because we just need some PVT. Bottom pressure has been updated for us. This is not a part of the exercise. There's a different course for that. Same with FMB and all these things. This is just a part to focus on analytical and numerical RTA, those pieces of it. So once we have the PVT and production data, we're ready to go to analytical RTA. And in this case, you will actually see that in fractional RTA, that your delta parameter, basically, it looks like it's in transitional flow the whole period. So this can be modeled in two ways. You can either use like a delta that's not 0 or that's 0.5, or you can use like a larger pressure-dependent permeability type of variable. And at least for the numerical RTA workflow, that's kind of what we're having to do there. So when we get to that piece, that's why I'm going to include a pressure-dependent permeability for this particular case. All the things we're looking at here will be the same as in the other cases. Not that much data in this case, but you see the same thing. As we go below the saturation pressure, boom, it starts to shoot up, and you can toggle this data off if you want to. And that's an interesting observation. It makes me a little bit like, oh, should probably be a little bit careful when we start to interpret pore volumes and these things. And this is actually a pretty interesting well from some other perspectives too. So that may be something we can discuss in another session. The thing I would like to focus on for this well is the numerical RTA piece. And in numerical RTA, we're going to do a couple of changes. And this is again primarily to show you guys some of the key inputs that are unknowns in general. And there's workflows to get more comfortable with certain of these parameters. That's the fracture gamma is one of them, and the rel perms. I'm going to start with changing the rel perm. We're just going to do the same as we did earlier with reducing the SWC from 20 to 10. And the Connaught water saturation, that's the irreducible water saturation. So the difference between SWI and this number, that's the movable water. Okay, and we're going to click save. And then in the matrix and fracture gamma, we're just going to make that parameter a very high parameter based on this delta parameter that we saw. We're going to make that 6. And then we're going to, so again, we're going to change the Connaught water saturation over to 10, pretty high matrix gamma. And then when it comes to the number of type curves, we're going to change this to 10 smaller models. And I'll show you what that impacts the runs here. So again, we've changed this to 10. We have increased our gamma a lot because of what we observed with the fractional RTA work. And then we'll change this to 10 smaller models, and then we're going to click run. Now we're running a lot of different cases at the same time, and we're basically getting something that looks like this. And now the reason why we have so many stems, right, is these 10 smaller models. The reason why we have so many stems is because we picked a 10 here instead of 5. That just gives us a little bit more resolution on the numbers here. Okay, and here we try to match the stabilized water cut. I think here there is definitely some kind of a well intervention event. I'm a little bit unsure what's going on here. So some uncertainty on that part of it. I think we could run the autofit, and the software will try to pick something for us. If we don't like that, we could pick something else based on our visual pick. Maybe this is not a bad pick right here, 2.5. Here we see our GOR is not so good, so maybe we would like to evaluate maybe a couple of the other stems as well. And in this case, maybe we should have gone in and probably changed a little bit of properties related to our rel perms just to get a little bit more gas coming out of solution. But this is a monster well, pretty high pore volume, and also a pretty large LFP. And again here, if I bring this into my numerical model, I know my cumes will be great. I know my water cut stabilized will be awesome. I know my cume gas will probably be a little bit under predicted. Looks like here, but that's something we'll see when we go into the last step here. That will be clicking yes, and then we'll run the gas piece right here. And these are the result parameters in this case. We have fracture half length 380, low matrix permeability, and this will be our history match on the first flow. And in this case, I saw, okay, wow, yeah, my pressure fit is actually pretty bad. My GOR is pretty good, and my cumulatives is also pretty good on the first run. My water is not good. So what I would do here in practice would be to go back to numerical RTA and make sure that I match my gas better here, because here I'm frankly not doing a really good job. And a very simple way to release a little bit more gas would just be to remove the critical gas saturation right here. The critical gas saturation, that's a gas saturation you need to reach before gases that comes out of solution with the reservoir oil starts to be mobile. So if I do that and rerun the model, hopefully I should get a little bit more gas coming out of solution. And again, if you want to know more about how you deal with these rel-perm parameters, we have that rel-perm cheat sheet provided in the appendix and also in the manual. And when I'm talking about this, if you look at this well, if there was a very dominant critical gas saturation, that would mean that as soon as you go below the saturation pressure, the GOR here would actually dip down before it goes up. And here we don't see that. So there's no evidence in the GOR data that we're dealing with the critical gas saturation in this particular well. So that's why I think it's justifiable to reduce that number to 0. And you see what that's done on our gas volumes. It definitely lifted it up and made it much better. If I want to pick something that was kind of similar to what I had, that will be this well right here. And now I'm seeing that my gas fit is much better. So in addition to using this plot, I'm of course using my cumes as well to make sure that my interpretations make sense. And then when I click export now, control on gas again, I should be able to get the much better BHP match than what I had before. And as long as these are pretty decent as well. Mo, anything to add here?
No, I don't think so.
Yeah, pretty good. So I don't know if there's any questions. It's been a long day, a lot of RTA. But, yeah, we did not mention that, Chris, and that's probably a little bit more in the realm of the whole kind of numerical model piece. But there's an autofit function in the numerical model. Some people, okay, let's leave RTA aside for a little bit. Let's say you uploaded PVT and you uploaded production data and you calculated bottom pressures. And you don't want to do any flow material balance or RTA or anything. You want to jump straight to the numerical model and start a history match. Then you can use this feature called autofit. And what autofit does is that you pick the parameters that you would like to vary within different ranges. So let's say in this case, by default, we have matrix perm and fracture half length as ranges. And then we provide a range that they can change between. And that is automatically populated based on what you already have selected. And you can increase this range if you like to. And then you can also change the weight factors. So right now I'm weighting oil and gas and bottom hole pressure. While I could also go in and say, I would like to weigh not only oil, gas, and bottom hole pressure, but I would like to really weigh the last portion of my oil rates, for instance. I think that's more important than anything else. And I think the early time, for whatever reason, I don't believe the early time data, so I can actually weigh that data to 0. So I can say I would like to set the weight to 0. Let's say the first 10 days, I don't want to weight that at all. Those days become 0 weighted and grayed out. And then in the autofit now, I can pick other parameters too, relative permeability parameters, etc. I provide the ranges and I click autofit. What the software does is running a regression. So we'll run this model time and time again until it finds whatever is the most optimal solution within that range of data. So in this case, it looks like it found some kind of minimum inside of that feature on the control, and then that's what it's going to try to do. So this will be like, okay, I don't want to do RTA, I don't want to do analytical, numerical, or whatnot. I just would like to go in and auto fit from the get-go. That could be a option to use right there. And what you're actually using, that will be dictated here by the screen. With that, just like to thank everybody for joining. It's a lot of people. It was fun to see. And then if you guys, you know, if we like to work on any of your guys as well together and these kind of things, we're always happy to jump on a call. So I'll stop the recording here, and then we'll talk as soon as we can.